So the topic of today is the challenges in the energy transition. And so we got, and as Gerrit said, my name is Sonja Monica Berlijn. I'm a professor in secure power systems at the University in Oslo, and I'm a full-time business director at DNV, which for the Dutch people, and maybe some international people, have bought up the KEMA for some time ago. So we all are aiming for a sustainable, secure future energy system, and the latest development, international development, have only strengthened that it is needed that we go in that direction. And also, of course, everyone wants to achieve the Sustainable Development Goals. So, but these are very nice words, but what does it mean in practice? So what it means in practice is that there is, in principle, 4 ways to achieve this energy transition. The first, maybe the biggest way right now, is by electrification. Then you have, of course, the replacement of fossil fuels by biomass. We can do, of course, a lot of carbon capture, and of course, we can go to hydrogen as well. But this massive electrification, what does it mean? Well, the numbers vary a little bit from report to report, but in general, everyone is in agreement that the need for energy will, let's say, either double or quadruple or 7-double. So this is not the means of, let's say, you have a car made for 4 persons and you squeeze in a 5th person in the middle seat. This is about how do we get the 2nd car to drive, or maybe even a 3rd car, or how can we make a bus? These are large changes. This means also that if the demand is increasing, we need to increase the production. And the renewable production, I used to joke a little bit about it, but renewable energy is quite often produced at the moment where we don't need it, at a time we don't need it. So we need it, we need to transport this energy, and therefore there is a need for increased transmission. Let me give you a very simple explanation of the electricity system, which may later on clear up a lot of your questions. So what we have is, let's say, the social cultural system that says that it's time to reach the climatic goals. It's time to have a secure power system. It is a critical infrastructure. We need to go to much more renewables. We have then, of course, a lot of disruption in the system. It's like weather, like wind, hurricanes, lightning, but it's also like people actively disturbing the grid, either by cyber security invasions or by actually cutting off cables. So we have the supply, that means all the production. We have the demand, that is, industry, households, data centers. And then we have a market system that connects the supply and demand, so that settles the price between the two of them. And then the market system will give signals to the control system, which is then usually one in a country, and then you have a combined for a couple of countries. And then, of course, on the lower levels, you have also a number of control systems. And then, of course, this when the market is in agreement, this supply and demand need to meet physically. And that's why you have the transmission and distribution infrastructure that nowadays also contains a lot of IT. And this disruption system and the social culture system, they're not, that's why these arrows are so big. They are not only, let's say, influencing one thing, they are actually influencing the whole system. So what can we see for trends in this system? Well, we see now that the demand is increasing by a factor of 2 to 7. We see that the supply is increasing because the demand is increasing, and then they want to have the supply met. Let's see. So, and a little bit back then to the supply. So in the last 20 years, we have maybe seen an increase in Europe, and these statistics are available for all over the world. I just happened to pick the Europe graph. is that we have seen the last 20 years, we have seen maybe a 20% increase of the electricity generation. Now we need to do at least a 300% increase in the next 30 years. So this gives a little bit perspective about the challenges ahead. It's not a small change, it's really a disruptive change we are standing in front. So what is happening here is that it takes much longer time to build a new grid than it takes to build new production and to transform the different sectors. Because, I mean, everything that can be electrified will be electrified because the price of electricity is so much cheaper than the price of fossil fuels. So what we see here also is that the typical deploy time, for instance, of PV and onshore wind, it's about maybe 5 years, but we see that it takes about, an average, about 8 years to build new overhead lines. And then you can imagine a little bit what's happening. You see that we have a demand with a response time about 5 years. You see that we have a supply system that's also able to respond within 5 years. But then we have this system in the middle with a response time above about 10 years. Another trend that is we see now is that the number of disruptions are increasing significantly. No, I think everyone has heard about all the cables being damaged in the Baltic Sea by Russian fleet. So what this means is that the grid that is actually in between is being very, very much challenged. It's burning, we could say, and the grid risks becoming the weak link of the energy transition. It is that there's so many projects on hold regarding, let's say, renewable energy. And also it's that, for instance, companies are complaining that they have to wait 10 to 15 years to be able to have the grid connection they are asking for. And for them, it's a little bit unsure if their business is still running at the time when they get the connection. So what we are experiencing is something that we have called gridlock. And as you understand, you see why, from a holistic point of view, why this is actually happening. So what are the consequences of this gridlock? Just to name a few. Well, we risk, of course, not reaching the climatic goals, and this will cost us more at the end because of the political instability that it's causing, but also because of all the cost of all the climate disasters caused by not reaching the climate goal. We see a reduced or delayed creation of new job opportunities. We might lose our competitive advantage, especially in some countries. Some countries have easier to do this energy transition than others. And because of the price of electricity is cheaper than of other costs, you will lose the competitive advantage. But we also see that there is an increased cost for like offshore wind and onshore wind project and even PV project because of uncertainty for the developers and for the investors. And then we see also a potential financial risk because of the flowing capital. So all in all, we see a lot of lost opportunities. And this is getting rapidly a bigger challenge. There are more and more attacks to the power system because everyone has understood that this is the critical infrastructure. The number one critical infrastructure is the transportation, and electricity grid is on the second place. But because the transportation sector is going electric, the critical infrastructure number one critical infrastructure will be very soon the electricity grid. This means also that we see an increased requirements towards the resilience and the availability, and not only because of new customers like data centers and steel and aluminium and more melters and other processes that are very depending on a secure power supply, but also the national defense in each country would like to see resilience because more and more is depending on electricity. And it is already known that, for instance, if a country loses the electricity for 4 days, this will turn into a very big chaos. So 1 day is okay, 2, 3 days is a challenge. 4 days means a very, very big social disruption. What we also see is that more and more AI is getting into use and integrated in the electricity sector. And these are huge loads. I recently heard that they're building like new data centers like 4 times 1 gigawatt. And 1 gigawatt in a traditional coal plant is maybe 60 megawatts. So these data centers, they are really, really huge consumers. And normally data centers are a very stable load, but when it considers AI, these data centers actually introduce a very intermittent load that introduce a lot of disturbances. And here's why maybe your help is needed, because here power quality will become an even more emerging issue. And what we see now is that because of all these trends and disruptions, both the new generations and a new supply, they are very nervous because they don't know if they will get the connection to the grid as planned. And what I see is there is just one way out, maybe 2. So, but we need more grid, and we need to develop this much faster than we ever have done before. And we need to utilize the grid that we have much better. And I think here your community plays a very, very important role. Back to more grid. So it's not only the developers for new supply and demand that are nervous, but it's actually also, let's say, the people that are planning the grid. They are also under a lot of, stress. They have to plan 20 years ahead, 30 years ahead, under very, very large uncertainties. The systems have become very much more complex with interconnectors, and it is also known that new connections don't solve actually all the issues. They are facing a lot of unanswered questions. For instance, the lifetime of a power line is about 60 years, while the lifetime for a data center, what is that? Is it 5 years? Is it 10 years? Might new, let's say, development make the large data centers overflow so that they're not needed anymore? So you understand when you have to build new connections and you're not sure that the load is actually there in 10 years from now, are you really is so interested in investing in this new connection? And there is also the reality versus the prognosis. For instance, we have seen that in Sweden, the need for electricity hasn't changed anything the last 30 years, even if the, let's say, the number of people connected to the grid has increased, the number of companies, industry that have been connected to the increase. And why? That is because of energy efficiency. So this is also something that we need to take into account. Maybe we see an overshoot now, and is it then needed to plan new grid for this overshoot if then the need for electricity will stabilize on a downward slope later on. But now we are where we are, and even if the total need for electricity will be stable, we see the need to replace fossil fuel plants with more renewable. So we need more grid, no matter what. So we see some technology responses to, so we see some technologies responses to these challenges. We see a large number of investments in new grids. We see the establishment of energy islands, maybe all over the world, with a lot of either AC or DC connections. We see long distance transportation, because to connect this large offshore wind farms or onshore new generation to actually where the load is. And we see also that there is a need for increased sustainable materials, and of course we have the environmental concerns. But also in planning new grid, there are some challenges. We need to look at system integrations. There are codependencies. For instance, if one country builds a new power line, that will affect another country. We see challenges in product maturity. We see a lot of conservatism in this sector. We see a lot of vendor lock-in, and that's a challenge. I will tell you more about that a little bit later on. We see challenges regarding human resources, because for all this transition, a lot of human resources are needed. And of course, we see challenges in the regulations and policies. So the other part that we can take, that is increase the grid capacity without new infrastructure. And this sounds a bit challenging, but this is actually possible. So what are some technical solutions? Well, it is better operational control. I will come back a little bit later to that. It is about updating algorithms and formulas. It is about going from n-1 to n-x, taking dynamic line rating into use voltage and temperature upgrading, use more dynamic system protection, etc., etc. So there are a number of technical solutions that we can use. There are, of course, also market solutions. It's like flexibility markets, flow-based markets. We can have variable prices, so explicit flexibility. So that means that we move the use of the electricity to when we have capacity in the grid. We also need to look at regulatory solutions, like different kinds of contracts. I will tell you a little bit more later about that. And we also shouldn't occupy more capacity than needed. And that's also a huge problem. So, and further, we need this right incentives for the grid owners and the grid operators, because nowadays a grid owner or operator get paid for building a new overhead line, but they don't get paid when they need to update their IT system. So, and this is more and more important because most of the solutions that I listed above require large investments in the IT infrastructure or IT systems of these grid operators. So then the question is, by how much can we increase the capacity? Is it is not 5%, it is somewhere between 10 and 50%, and this is really huge. And how come, actually? Well, you should look at a power grid as like, in this case, then on the picture, a four-line highway, where we actually drive just on two of them, because there is a slight probability actually that there will be a hole on the two lanes that we're driving, and then we need the other two lanes as spare capacity. But now with the digital insights that we have, it is actually able to predict when there will be a failure, and it is also easier to monitor all the traffic going on. And by that, we can, maybe in a time where there is a very low risk for potholes or sinkholes in the road, we can actually use the roads that are available. So another thing that is possible, for instance, is dynamic line rating. And by that, we can free up 30 to 40% of the capacity. And in my opinion, that is mainly caused by the fact that the power lines are operated with very conservative formulas from the 1950s. So we have formulas in the 1950s that have calculated how much a line will actually sag based on the current that is going through. And these formulas have never actually been challenged or updated. And now we have systems to measure both very accurate, the current going through the line, but also the sag. And then we see, hey, these formulas are actually wrong, or the wind is actually varying much more than just one parameter the whole year around. And in some cases, we can free up actually 30 to 40% of the capacity. And this is really a lot. Then we come to the fact that the grid is planned, maintained, and operated according to the N-1 principle. I usually tell that if people would stand in queue to enter a motorway, and they would see that just one line of the highway is being used, everyone would protest. But since this is not visible because it's electric, no one is really complaining because it's so few people who actually understand how all of this is working. So then another thing is that the security settings in a grid, they are very static. And we need more, let's say, more dynamic protection settings. There are some study going on. And of course, we need to have much more insight in the system. And when we combine this potential that exists in the components on the system, the whole system can actually be utilized much and much better. So what is the bottleneck actually of all these technical possibilities? It is actually the control center. And every new connection that we make will lead to a new situation for the operational control and needs to be trained. We see with all the intermittent, both consumption and production, we see much more unexpected events to happen with less time to act. So we need to fully automate the protect and control and operation of the system. And we also need to challenge all the regulations and conservative rules that are made actually for all technologies. These rules, they are from the 1920s, 1930s. We have new technology now, and we maybe need to update the new rules. So the development of the control center, if all these rules come from a time that we just had a single light to show if the line was off or on, but now we have much more information available. And that makes also the situation for the operator, of course, very complex. So maybe we need to go to, a much more automated future. So this about the n-x, n-1 to n-x, we can use much more spare capacity if we manage the risk that we have, because a risk is a function of the probability of something to happen and the consequence of that event. And now with new technology, we can reduce actually the consequence of an event, and that's why we can allow for a little bit higher probability for something to happen. But these principles, they haven't been updated, you could say. So nowadays there is, measurements and software available to actually calculate the actual risk. So that's why I would like to challenge also that instead of, running a system in the blind and just thinking that you have n-1, you should plan and build for n-1, but maybe not operate according to n-1. And then you actually see that the risk varies quite a lot during the day, during the month, during a year. And this is something that you actually can use. So what is needed for implementing all the technologies that I just have explained? Well, we need to have better control of the infrastructure. The margins in the power system will be challenged. So we need to have accurate real-time information about the status and the condition of the infrastructure. We need to know that some things will break in 1 hour or 2 hours because we can take measures in time. We will see much more AI and data transfer and interaction. Many people think AI is something new. And I'm sorry to have to disappoint you, but AI is already in use for more than 40 years in a power system. A power system would not run in its current form without the AI that is already in the system. All these new technologies, they require a high degree of digitalization, and that means that we introduce a new risk, namely the one for cyber threats. So the system needs to be cyber secure, and we need digital and cyber resilience. So to achieve all this, to achieve the climatic goals, to achieve a good energy transition, to make the power system secure and resilient and a reliable critical infrastructure, enormous amounts of reliable and accurate measurements are needed. And that's why I'm so very pleased to talk to you today, because I want you to see how important your role actually is to the overall well-being of our planet. So, and I also have been doing measurement myself, and the challenges actually in this system is that what we need to measure, they are very small and very fast signals, but also very large signals and very slow signals. We need to measure them on a remote location under extreme conditions, maybe -40, -30, you know, in hurricanes and whatever, because the last thing that you would need is that the first thing that will drop out is actually your measurement system. Because when do you need the measurements the most? Well, that's when you are in crisis, because when everything is smooth, the weather is fine, I mean, the system is running as it is, you need the measurements the most when you are in the crisis, and that's why it needs to work. So the takeaway from my presentation today is that our common goal is to create a sustainable planet. We would like to have a sustainable, digital, secure, carbon neutral energy system with the digital electricity grid as the backbone. It is one of the enablers actually of this energy transition. And to be able to tackle the challenges with these transitions on such a short term that we're talking about, let's say in the coming 5 years, we need measurements of all kinds on all places with good accuracy, and they are becoming more and more important. And that was the end. Thank you very much for your attention.
Thank you for the opportunity. I worked for National Measurement Institute, the high voltage lab, for many, many years, I mean, a few decades. So my topic today is the high voltage testing. This is a very, very small topic in comparison what Professor Berlijn talked about. But if you zoomed in, you will see there's still a very, very broad area of topics. So what I've done is I chosen some topics that I think will be interest to the general electrical measurement communities. And hopefully the talk will give you a general appreciation or high-level appreciation of what high voltage testing is about. Right, let's get started. So first of all, I'll give you some ideas about high voltage equipment in the grid or power system, or you call it electricity supply network, whatever you will call it. And then I will discuss the relevant international documentary standard, not the artifacts. This is a paper standard relevant to HV testing, IEC, IEEE standards. And then we'll discuss some specific techniques and measurement capabilities, different voltage types, and how voltage is generated, what are the typical measurement circuits, and of course, measurement traceabilities and measurement capabilities. And then along these topics, I'll introduce some of the recent development relevant to this future electricity grid theme. So a few of them like fast transient test, ultra high voltage UHV, DC measurement, high frequency calibration of transducers. A couple of presentations on that later today as well, I noticed. So this is not to introduce a electricity grid, just give you some idea of the high voltage, what levels we are coping with. So you have the transmission network, mainly high voltage or ultra high voltage, which defined as system voltage about 800 kilowatts. So the equipment there typically, depending on the country or region you're from, is 145 kV to 1200 kV. And then you have another major part is the distribution system is from 145 kV down a few kilowatts. So the equipment in this gigantic grid apparently experience working voltages, and so you need to test them right accordingly. This is what high voltage testing about. So this is the focus of today's presentation is the testing for the grid, nothing else, not for say physics study or whatever. So give you a few examples of this equipment. So on the left-hand side is a type of transformer called phase shifting transformer. This is actually quite a current topic because more and more of these are coming into, they are old devices, but more and more of them come into the network because of the network complexity. You need to shift power around more often, so change direction. So these are the devices that come in quite often, more and more. And this is a close-up. It's a big apparatus or equipment. This particular one probably 300 tons, but there are much bigger ones. One single phase, so 1200 kV transformer is about 800 tons. So we are focusing the insulation of these devices, such as the transformer. So you have internal insulation, electricity insulation, which is oil, paper in this particular one, and the external insulation, these bushings for connection to electricity grid, are polymers. So the testing we are talking about today, or in high voltage general, is really just for this testing the integrity of this electrical insulation, right? So that's a very important point. We need to remember that. Some other examples, you have circuit breakers. They're not like this wall switch, they are big. You have current transformers for measuring up to a few thousand kiloamps of current. You have transformers for measuring the voltage. This particular one is called capacitive voltage transformer. Of course, you have a magnetic voltage transformer as well. So all of these need to be, their insulation need to be tested to ensure they work properly and safely. They are not only working in the network of voltage, like 330 kV, whatever, they also see lightning strikes. They also see switching pulses generated by the circuit breakers, right? Or other type of switching devices. So there are quite a few other voltages that be used in testing, not only in the AC or DC voltages. So where are the testing done? Of course, we can do the testing in the manufacturing plants of this equipment when they are quality controlled before shipping out, or in the design stage, or in the substation just before the commissioning. But another very common place we do this testing is called high voltage laboratory. I'm sure many of you have seen this type of laboratory. This particular one, you have, say, 45 meters long, 25 meters wide, 90 meters high. It's a medium-sized high voltage lab. So they're much bigger ones. And this particular example, you can see the transmission line generate insulators with a simulated part of tower are tested for the withstand of lightning strikes. Under rainy conditions, you can see the pool here collecting water. So that's just a very brief picture of high voltage testing to start with. Now let's have a look at the specific testing standard. So which are very important for the testing, high voltage testing. This IEC 600 series is a very top-level general standard for define the testing terminologies, testing procedures, and the measurement requirements for all high voltage testing. So there's a top-level standards. And this particular standard is called a partial discharge, which is also important. You don't see partial discharge normally at a high voltage. I'll backtrack. Partial discharge is for high electric field insulation. So in the high voltage field, the electric fields are normally high. That's where you have partial discharge, which is minute discharge in electric insulation that will eat away the insulation over time. So all the equipment need to be tested for this minute discharge. So this is the important measurement. This 61083 series is mainly for instruments and low voltage instruments and software used in high voltage testing. So we have a few keywords highlighted in red. So the impulse is special for high voltage testing, and software is very also specially need to have special intention in high voltage testing. And I mentioned alternating direct voltages. So what's the fuss about that? That's everybody use that. But the AC and DC voltages in high voltage is quite different from what you get from, for instance, 5700 calibrator, right? It's nowhere near that pure, right? And that's why the instrument needs to be able to measure this complex with distorted waveforms. And you need software to calculate the correct voltages. And that's why you have these standards. So I give them list here, so it's just for your later reference. By the way, I'm happy for the video to be shared, and also I'm happy to share the PDF of this presentation. So standard, also you have equipment standard where the HV testing are specific requirements are specified apart from those general standard. This standard is important because it specifies, it's called insulation coordination. It specifies the voltage levels in the power systems. You can't just have arbitrary voltages. We know at home we have 230, the same in the high voltage. You have only a number of voltages that can be used. So that standard, that's important in understanding the high voltage testing at the different levels. You have another important standard for power transformers and switch gears, insulators, the many standards for insulators. They all specify specific tests. And another big series, many, I think now probably more than 10 or close to 20, about the instrument transformers which are for measuring the current and the voltage. They're not for transport delivery power. This is for measurement purposes. And nowadays you have digital ones as well. Okay. Now let's have a look at what type of high voltages are used in the testing. So first of all, AC. So AC tests are for all AC equipment, no exception, except HV cables. There's reasons for that. But the value you use to test is peak on root 2, not RMS. And the measurement needs to measure peak on root 2 and a number of factors called crest factor error, which is the difference between peak on root 2 and RMS. And also you need to know the difference between the positive and negative peak, because in the actual voltage testing, the insulation responds to peak, not RMS in most cases. That's why. And DC used for power cable and DC equipment. DC equipment is becoming more and more prevalent in the network. So what you measure, the mean value and ripple factor. A lightning impulse is simply a simulation of lightning strikes, but standardized waveforms, such as, do you see that? Okay, it's a fast 1.2 microsecond rise and about a 50 microsecond time to half value. So it's quite fast pulse, but it needs to be used for testing all equipment. The parameters to measure the peak voltage and the time parameters. But these voltages determined by a standardized algorithm. You can't use your own. That's the current standard. We'll talk a bit more later. And then you have the operation of circuit breakers and disconnectors. These equipment generate switching impulses that will put extra stress on the equipment. So this also standardized type of impulse used in the laboratory for testing equipment. And you also have the short and steep front, which is a new type of, it's not really new, but it's another type of pulse, much faster than the lightning impulse. which has a typical rise time about a few hundred, 200 nanosecond instead of 1,200 nanosecond. So again, peak voltage rise time, and the standardization in this area need to be further developed. Other quantities that you don't see in the low voltage measurement is the partial discharge. As I mentioned, all HV equipment need to be tested. You test the so-called apparent charge, the minute charge that in the insulation system, and the partial discharge inception voltage. At what voltage level they start to have this partial discharge. Another quantity or test is the radio interference or corona. The corona is the external discharge on high voltage terminals. So for instance, or high voltage conductors. So in transmission line, you have, say, some fittings like the line spacers. On the high voltage, they will discharge. And this discharge create radio frequency, high frequency interference to the communication network, radio broadcasting networks. So these need to be kept below a certain level. And that's why all these line fittings and many other equipment need to be tested for this quantity. And the other test is the dielectric dissipation factor, which is a measure of the loss or heat generated in the insulation. So you don't want too much heat generated. You don't want to have too much loss. And that's why this is also tested for most equipment. Another fairly new type of test is a very low frequency, which is not that often see in low voltage field, is 0.01 Hertz, 0.1 Hertz. Is for testing plastic cable, cross-link polyethylene cables, because they don't like DC. And you can't drive cable with AC because they're high capacitance, and also long cable. Okay, so these are the quantities. This nowhere near what we actually need, but this is majority of the quantities we need to test. So how do we generate, first of all, these high voltages? This is the example how this voltage is generated. So this is a short shunt reactor, 330 kV, 362 kV, and you need to be tested for voltage withstand under AC voltage, that level. So in this test circuit, what we say quite often, the test object is part of the voltage generation circuit. You can't generate the circuit without the test object, not like a calibrator. Doesn't matter whatever connected. Simply because it's a very heavy load. So in this particular example, you have an excitation transformer. You have a few four reactors, air core reactors, put in series with the excitation. So by changing the air gap, you change the inductance, and by varying the inductance, you achieve resonance with the capacitance load, and that's how you generate the voltage. So that's very useful, because otherwise you need to carry a gigantic power source, right? Which not that often available for on-site testing in particular. Okay, this is another example in the laboratory. Say this is circuit breaker. You have bushing, you have some capacitive load, not too much at the moment, but this transformer, testing transformer, has a compensation reactor set to can be set to different settings to compensate the load. By the way, in high voltage testing, majority of the load are capacitive load, and that's why these testing source always have reactor as a compensation. In this particular test, not only the withstand, we also did the partial discharge test. So in partial discharge test, this is the source, this is the voltage divider, and connect to the low voltage meter. There's another extra device called coupling capacitor that couples high frequency partial discharge to the partial discharge detector. That's how you test the partial discharge. This picture here, it just shows the minute, many small discharges. You can see that expressed in the picocoulombs. So the sensitivity of the PD detectors normally say a couple of picocoulombs or less. This is another example, very good example. Say this is a so-called synchronous condenser. It's 120 mega VA. Synchronous condenser now, like the shifting phase shifting transformer, are getting more and more used in the power network. It's because of the renewable energy. Basically, it provides inertia, additional inertia to the network. Its design is very much like a generator. So this is would be what it look like inside. But this is a big case, right? It's just a big rotating machine. So it's gigantic load. So this particular one, 1.1 megafarad. But the loss is very low, so reactive power needed to test is very low, and test voltage 25 kV, and frequency you can vary between these two extreme. So required test power is over 200 kilo VA, right? Big, but the reactive power requires only 6.5 kilowatt. So what you can do is to use a variable frequency source, 25 kilowatt, and excitation transformer somewhere here. And then you use a set of reactors with the reactance matching the capacitive reactance of the test object. And then you, by varying the frequency, you more or less line these two reactants close to 50 hertz, but you can never match that well enough. And so by varying the frequency, you can tune the Q to get your required voltage. And so that you don't, so only this small equipment can supply this gigantic machine. The matching in this particular is done so well. So in the end, we didn't need to use a variable frequencies. We just use a normal 50 hertz main variac. So this is a very good example how the voltage are generated for testing this big text objects. This is an example of calibration. This is a calibration of a GAS insulated, SF6 insulated voltage transformer. It's also a calibration, the accuracy test or calibration, because you test the voltage error and phase shift. Again, use the resonance set excitation transformer. Because the load is few nanofarad, it's still quite big, and the voltage is quite high, and the reference capacitor is the back. This is the voltage measurement. I won't go into too much detail. Just give you an idea about the voltage generation, which is important. So another very important topic for HV testing is so-called linearity test. Is this in the way? Yeah. Oh, okay. So quite often the voltage is very high. How do you make sure your measurement equipment can measure that high voltage with the confidence? So, but the reference quite often can't cover the operating voltage of the measurement device in testing. So IEC, this standard come up with the idea that you calibrate the readings of your measurement system at in the high voltage end, so you can calibrate for the ratio or for the reading errors at the voltage up to 20%, down to 20% of the operating voltage. Then you do the so-called linearity test, And the linearity test is done by comparing the reading of your measurement system to the reading of another reading device, whatever that can be, right? And the ratio at the different levels, and you can work out, and then you work out the maximum deviation of the ratio from the ratio at the lowest calibration point. So that deviation becomes a uncertainty contribution to the uncertainty budget of the subsequent use of the measurement system for testing. So this ensures that you have adequate calibration uncertainty. But if you can't achieve the uncertainty in this value below the acceptable level, that doesn't mean your measurement system is not linear enough. It just means the other device, either of the device of the measurement system or device you use for the linearity test is not linear, right? So you just have to try another method. The rationale for this approach is that if you get this linearity, non-linearity value low enough, the likelihood of both devices not linear is close to 0. So if you get a linear response, that means both devices are linear. So that's the rationale. Okay, we have that tool, then it becomes very useful. So this is an example. Say this device is what we say 500 kV AC measurement. We have a 100 kV version 3T can only go up to 100 kV. So you calibrate the readings of that or ratio of that divider, but then you do this so-called linearity test. In this particular, there are many ways you can do this. This particular case, you use another called linearity test reference, which is just the electrode with a low voltage capacitor. So this electrode and this low voltage capacitor forms another voltage divider using the air capacitance between this electrode and all this high voltage electrode. So this means you will have enough sensitivity to have another reading. So this is very useful. There are many other ways. I'm sure the high voltage expert have many other ways, but this is a convenient, one of the convenient ways to do this calibration plus linearity test. This is another example. Probably show that first. So this 2,800 kV impulse divider, which is a capacitor divider, needs to be calibrated. So the reference only go up to 1,000 kV. So you measure the reading or ratio of that up to 1,000 kV. Then you do the linearity test. In this particular case, the linearity test is done by comparing the reading from this measurement device with the reading of the charging voltage of this generator capacitors. So these are the capacitors for charging the impulse generator. You charge them in parallel, you switch them into series to generate the high voltage pulse. But the reading of that charging capacitor voltage, which is DC, can be used as another linearity test reference. Quite often, that works if you do that properly. So to give you another example. Okay, so we have calibration devices. We can do the linearity to cover the operating voltage of the measurement system. But how do you establish the traceability of your reference? Now we'll talk about a few examples. So first of all, this is a lightning impulse. So lightning impulse reference normally consists of a non-inductive resistive divider and the low voltage divider and a digital or digitizer or digital oscilloscope, right? So the IEC method says that you can calibrate components of these devices. right, for your reference, because or you can do simply compare another reference. For AMIs, basically you need to do the components method. So you measure the resistance or low voltage ratio of these components, and you measure the linearity resist divider up to 400 kV by comparing another. This is not the linearity we talked about before. This is real linearity against another reference divider, which normally will have a different design, or it can be capacitive or capacitive. And then you do step response to ensure the dynamic performance of these devices that can have enough bandwidth. And then you calibrate the so-called dynamic scale factor of digital recorders that to measure these pulses. So these are the low voltage dividers. And then you make software, compare the software output of your system with IEC reference values from the IEC software reference data generator or impulse data generator. And then you do international bilateral comparison, like many other fields of electricity metrology. So if you do this, the typical CMCs, AMIs, be 0.5, 0.4, expanded uncertainty for voltage up to 700 kV. So the software give you idea how that was performed. So this IEC standard has a software package. It can generate software testing standard to suit your digitizer specification. And there are about 12 analytical waveforms with known values of the reference values, and also 17 measured waveforms, also with known reference values. But these reference values are obtained by robin intercomparison among many organizations, most of the AMIs. And then you perform international comparison, quite a few done in recent years. I mentioned this one is Euromet 3-run comparison, 20 laboratories across the globe, and more recent ones, I think the report just came out a few years ago. So you have a divider, your home laboratory. This is the transfer divider, and this is the typical front. You can see it's nowhere near smooth. So this will put extra uncertainties into your measurement. So this is result for the second comparison. You can see this is a peak value difference from the so-called transfer reference. The reference value uncertainty is 0.4. A lot of laboratories exceed that. So some of the CMCs are a bit ambitious. I think the reason for that is because the voltages are produced by individual laboratories. They have different noise, different dispersions. That put extra uncertainties into the results. And now it's definitely the PD AC peak voltage measurement. So RMS, we know how to do that. It's quite often, quite easy. Not easy, or quite well known. So you basically you have digitizers to digitize the waveform, and you first need to determine the ratio of your HV device, either as a voltage transformer capacitor divider. That can be done fairly accurately, and then voltage linearity also, say 0.1, 0.05%, and then frequency response. You need to measure frequency response of AC dividers because they not the waveform, the physical component allowed up to 7 harmonics, I think, in IEC standard. So you need to be able to measure a wide range of AC. That's why you need to measure that. And then you got to evaluate your digitized voltmeter. And some people, I can see the Europeans use quantum Hall voltmeters and calculation softwares. You also need to verify your software because these are not pure sinusoidal. They got harmonics and different funny waveforms. So by doing all of these into comparison, you can easily already achieve 0.1% CMC for peak current to up to 1,000 kV. So again, comparisons, you got a few rounds, international and bilateral. So this one done 11 AMIs up to 200 kV. And so this is the result, which is not that ideal because of some issues with the waveforms again. But since then, the Finland and PDB done a very good job. They have published paper. They achieved a 50 ppm agreement, yeah, for up to 150 kV, which is outstanding achievement. MIA did some comparison with VTT, the makers, just the low voltage digitizer and software, which is a very significant part of this whole measurement system. So we achieved within 10 ppm for pure sound wave. For triangular, which has a lot of distortion, got 170 ppm. So, but this is more than enough as a reference. The uncertainty for HV peak current 2 testing requirement uncertainty is only 3%. CMC for most MI is 0.1. We say low voltage digitizers software issue noise are main uncertainty contributions. Right. How we go with time?
There's another 3 minutes.
Right. Okay. Another example is the fast transient. Again, you measure. Oh, this is a fast transient. Yeah, you measure the step response, and you measure. You do, and in here you do the deconvolution of the recorded form and the waveform calculated by the deconvolution. You can see the fast pulse with 94 nanoseconds rise time, you achieve about 1% difference. For slower pulse, it's a 0.5%. So for this very fast pulse, we can also confidently measure within a couple of percent. And then this extra work, you compare with the low voltage divider, which is 10 kilovolts, which is faster. And this is your fast transient divider, 350 kV. And this fast divider has much faster step response, 2.5 nanoseconds. And then you compare these two at low voltage, you get almost same voltage. Say the front is about, I got blocked here. Okay, 150 nanosecond, you got a difference of 0.8%. And then we also done, say, in the comparisons, in the fast transient field, so VTT MRA, and the different, you can also for fast and the slow. Fast is about 100 nanosecond rise, so slow is 160. It's just less than 2% difference. Okay, another recent development. I think we have another presentation in this field. It's just wideband calibration wideband instrument transformer or current or voltage sensors. In our institute, we done with superimposed the harmonics up to 10 kilohertz, not the sweep the harmonics, but superimposed. So that's what we achieved. The components you can see, basically generation is from waveform generator with the amplifier or step-up transformer fit the low voltage end of high voltage transformer. And the reference is capacity divider. This is device under test. I'm sure you'll hear about more in the other presentation. So another recent development is really about HV for transmission. Many advantages. The longest we believe nowadays is 3,324 kilometers long and 1100 kV, 12 gigawatt. So these are the important devices called in the inverters, converter stations called valve halls. They do the conversion of DC to AC. And for measurement in the network, DC network, these are the divider designed in China, 18 meters high. But AMI's done a lot of work for reference. And this is the 200 kV divider, I think PDB, they say the Swedish RISE. They achieved tremendous feat. 30 ppm, 1600 kilowatts, and 20 ppm at 1200. MI did some years ago, 1000 kilowatts, 100 ppm. Okay, conclusion remarks. So HV testing circuit are customized based on paces. So the test objects are part of voltage source. Linearity is an important tool in validating uncertainty in the HV field. HV field waveforms are complex. That's why you need software testing. The HV committee is very active, you can see, to serve the HV testing field. The recent development listed here, we don't want to repeat. And I just reiterate some of the ideas that by Professor Berlin. We need more testing, for sure. Okay, thank you, that's all.
Thank you for the introduction. Good morning, everyone. My name is Stefano Lodetti. I'm from NPL, but I'm here now wearing my hat as chair of the European Metrology Network on Smart Electricity Grids. And I'm going to give, as Gert said, a bit of a vision on how we see the research challenges in the electricity grids in the next 5 to 10 years. So I'm going to start with a bit of an introduction on what it is, the European Metrology Network for Smart Electricity Grids, a long name. But then the main part of the presentation will be on our strategic research agenda. And then I will give a quick overview of the future steps in research. So European metrology networks have been created a few years ago by Euramet to develop structures, sustainable structures in areas that are considered of strategic importance for Europe. And the idea is to build the next level of cooperation between member countries. And the objectives are to create and disseminate knowledge, building a coordinated infrastructure, and ultimately maximize the impact of our research and development to European industry and society. So amongst these areas of strategic importance, there is the smart electricity grids. So our scope covers all the measurement related to the electricity grid in support of the energy transition. So mostly electricity measurements, but not just electricity measurements. And the main objective is to create a solid engagement with stakeholders in the grid to identify what are their needs, what are the challenges, and how research in metrology can best support these challenges. Here you can see on the right-hand side that the members of the EMN, of the Metrology Network, most of the NMIs in Europe, but we also are open to partners. So we have at the moment 3 universities that are partners in our network. And here you can see a list of the stakeholders that provided formal support to the creation of this network. As I said, stakeholder interaction is one of our main objectives, and maybe the most important outcome of the work we've done so far is the creation of this document, a strategic research agenda. It's a document that collects the needs of European stakeholders, translates them into what are the major metrological challenges that are faced by the stakeholders. And the objective is to ideally steer future efforts in research and development to address these challenges. And ultimately, the idea is to underpin the competitiveness of the European Union. This is a little bit of the process of how we came to the realization of this document. It took a few years. It all started with the expertise from the metrologists in our network. Some of them are sitting around this table. But then the major part of the work was an extensive stakeholder consultation. This started with online surveys that they were followed up by one-to-one interviews. And then we also held 3 workshops where we engaged with mainly industry, government bodies, and universities. And after collecting all that information, there's been a part of consolidating the information into a document. And then finally, in the summer of 2023, we published this document, the Strategic Research Agenda. The agenda is divided in 9 major themes that we have identified where we think there's a need for future research and development. This goes from grid monitoring and data analytics, grid integration with other sectors, in particular with gas, the digitalization and digital substations, high voltage testing. We've seen a presentation already on how important this is. Another growing area is DC grids and DC application, very quickly growing. Revenue metering has been identified as a very relevant topic, especially for government bodies. The quality of power supply, which is a traditional area of metrology that is evolving very quickly. Instrument transformers and sensor, and then efficiency. Now, this is a bit of how the agenda looks like. I think it's a very easy to digest document. We tried to keep it as compact as possible. So for every theme, there is a landscaping, and then we've identified a list of challenges. And what we've done, we've also created these implementation roadmaps where we try to map out how these challenges will need to be addressed in the forthcoming years. And now I'm going to go into this implementation roadmaps. This is the one for power quality. You will see they all have the same structure. They're divided in 3 areas. In this case, we have characterization, harmonics propagation, and disturbances propagation in general, and standardization. And then for each of these areas, there's a timeline that spans about 10 years. And then the exercise that I want to do today is to show how the research projects that have been done in the past year and that are now ongoing or upcoming are targeting these areas. So you will see logos of EU-funded projects and the areas where they develop most of the research. For instance, one big area is standardization for specific applications. It's a bit generic, but this covers DC grids, for instance, and we've had a project that just completed about DC grids, but also other areas like railways or large ships where DC is becoming increasingly relevant. Another big areas is the frequency behavior of the instrument transformers. As the power quality landscape is changing, the instrument transformer will need a better characterization and also to understand how disturbances propagate in the network. And I'm not going to go into everything, but I just want to point out there's another aspect here related to how power quality and the changing of the grid are very related. We're going towards grid with lower values, lower levels of inertia, lower level of short circuit levels, and that affects the power quality. And we will hear a presentation from my colleague Deborah later on the relationship between power quality and future grids. This is the roadmap for DC grids. Here you can see again for 3 areas: characterization methods, for devices, for instrumentation, for metering devices. There's also an important area of new definitions where again, for instance, power quality is very relevant. Power quality is evolving. Power quality used to be defined in AC systems, but as we have more and more DC system, what does power quality mean in DC system? So there's been a need of developing new indices, new indicators, understanding whether AC indicators were suitable for DC or not. And the DC grid project, for instance, work intensively on it, but there's still a lot to do. And the role of DC charging station, so fast EV charging station, is very relevant. And then there's, again, the entire area of standardization that feeds directly into regulation and is of high priority in Europe at the moment. This is for data analytics. We've heard a presentation this morning of we're getting more and more data from the grids. Grids are increasingly populated with sensors, but there's still a big question on what do we do with the huge amount of data that the operators are receiving. And we have a new project that is starting this summer that will look into some of these aspects, including, for instance, the quality of these data, the control of the data that's coming from sensors. Can they be combined? How reliable they are, and then how they inform big data analytics. How do you visualize the data? But also looking into machine learning applications, for instance, for short-term forecasting. But obviously, the data analytics, as you see, is much broader, and there's still a lot of research that needs to be done. And a big area that we were discussing during a coffee break that will require more metrology is the modeling. A lot of grid operation is based on models that are increasingly complex, but there's a big question on how you validate those models, if they're not fed with the right data, what kind of results do they produce? So this is another big area of development. So data analytics is strictly related to the monitoring of the grid. So here you see again a lot of challenges in this area related to the line rating, the state estimation, with the objective of optimizing the use of the grid. And also there's another big area on measurement equipment, how they are suitable for the grid monitoring. And here again, we have projects coming up. All of these projects are very, very new, detecting new effects in the grid, characterization of the new features of the system, of extended frequency response of devices on the grid, another big area. And we've included in the grid monitoring secure timing. Timing is becoming increasingly relevant for grid monitoring. And there's a lot of aspects that need to be looked into, like the secure timing protocols, calibration of timing protocols. This is another area, instrument transformers, that is quite traditionally metrological domain. As the grid evolves, as the features of the grid change, the frequency of the phenomena change, we need to have fit-for-purpose instrument transformers. And as I was saying before, the instrument transformer generate the data that then we use to make decision. So we need to trust the instrument transformer, we need to trust the sensors that are on the grid, and we need to make sure that operators use them for the right purposes, because maybe a device was created many years ago for a different purpose and not necessarily suitable for other applications. And here I have highlighted this instrumentation for higher voltages system, and we're gonna hear a presentation from Mario on the ADMIT project that is looking into characterizing instrument transformer for an extended frequency bandwidth for higher voltage levels, which is a big challenge in the grid. Here we have digital substations. As the grid evolves and becomes more and more digital, the role of digital instruments and digital substation is becoming increasingly important, especially in certain countries. And we've identified 3 areas of work. One is, again, standardization, being a very new area. There's a lot of development that need to be done, but there's also new technologies, including time protocols, for instance. But all of that goes alongside with the need for new measurement techniques and methodology. And here we had one project that is concluding this year, which is called Digital IT. that looked into some of these challenges. But as you can see, there's still a lot that needs to be done in terms of digital substation. And here we put cybersecurity as a big uncertainty, but still requires a lot of attention. Another area that's particularly important is the revenue metering. As you can see here, again, there's a lot of work that needs to be done. One of the big areas that requires effort is the metering in DC systems. This is particularly relevant as DC grids become more and more widespread, but also as we are extending the infrastructure for electric vehicle charging. So there's a big question on how you go and build electric vehicles when they charge, rapid charging. More and more, we're seeing more and more high power charging station that require a lot of power. And there's a big question on how you test the meters for this huge amount of powers. Is phantom power enough? Do you need to measure real power? And I've highlighted this because this afternoon we'll hear a presentation from Helko from VSL about this project, Metrology for EV charging station, that will look, that has just started and is looking into some of these aspects for electric mobility, very relevant. High voltage testing, another very important aspect. This obviously requires big infrastructures. We've seen the presentation before from NMIA. You need big labs, big facilities, but as the grid expands, as we see higher and higher voltage levels on the grid, we need to be able to keep up with the pace of the grid development. So ultra high voltage is a big field of development. Ultra high voltage testing going above a megavolt, extending the traceability of the NMIs in that area, but also defining standardization for what kind of waveforms you test, what devices need to be tested, so cables, AC and DC switches, partial discharge, and that goes alongside with measurement techniques. So we've seen it this morning as well, very low frequency that requires specific testing techniques, very long times. So all of these require testing, and as you can see, we have many projects that are looking into high voltage testing. And last but not least is the efficiency. Efficiency is of high relevance for the EU as we move towards greener systems. But that is clearly, it's very easy to see how that's underpinned by accurate metrology. We need to understand the efficiency of components, especially as we go with very high level of efficiency. The losses become very small, and that requires higher and higher levels of accuracy. So that is a big area of development. Power converters, for instance, is an example. But another big area is the capability, because as the grid evolves, as the electrical signals become more and more complex, we have more dynamic power. Then we need to be able to test the efficiency and the losses, not just at the power frequency, but on an extended bandwidth. So that creates a lot of challenges. So we need to be able to test highly distorted waveforms, dynamic power, harmonic power. What does it mean? What's the definition? And then another area of development is systems. We have new systems that we're getting connected increasingly in the grid. So we have DC substations, we have storage system, batteries, but also supercapacitors. So we have projects that are looking into those areas. For instance, the e-trainee looking into the efficiency of DC substation for railway systems. We have a project on characterizing supercapacitors that provide storage to the grid. And at some point, someone will have to look into the efficiency of power to X conversion, for instance, electricity and grid coupling, and how is the efficiency, how is that determined? So that's an overview of the themes that we have identified. As I said, I think the document is relatively easy to digest, especially if you look into one or two themes. So I would encourage you to go on our website. You can navigate through the themes, but you can also download the full document. So this is available here, but you can also Google EMN Smart Electricity Grids, and hopefully you'll find it. This is a document that we published about a year and a half ago, but the electricity grids are evolving very quickly. So we need to maintain this document to keep it up to date. And since this is based on interaction with stakeholders, the update of this document will need to be to go through engagement with stakeholders. So we have different ways to do it. Last year, for instance, we had a 5-day event where we had several meetings and we invited stakeholders to give thematical workshops. We also had like moderated discussions, and that is a way for us to keep the engagement with grid stakeholders and keep understanding whether we're on the right track, if our research is aligned to their needs, and if whether something else can be done. So hopefully this year we will have probably another event, probably online, and then the idea is for the next year to have another big in-person event. Now very quickly, because time is short, but I wanted to give a flavor of the project that are active at the moment. So these are projects that are active or towards their final stages. Digital instrumentation, digital IT, sorry, for metrology for digital substations. We have an e-trainee project looking into energy efficiency in DC transportation systems, and ADMIT, and you will hear more about ADMIT later on, which is the characterization of instrument transformers on an extended frequency range. Then these 4 projects has just recently started, I believe last summer, looking into energy supply reliability, electric vehicle charging systems, and metrology for supercapacitors and their characterization, static and dynamic characterization, and sample by sample waveform uncertainty computation. And then this is a new slide. We have 4 projects that were recently funded with our European funding schemes that are about to start this summer. So we have one, the ELIT project led by PTB, looking into the metrological infrastructure for testing electrical insulation and high voltage. We have the Grid 4, which will look into the measurement infrastructure for grid forming converters. These are key devices that are the promise to deliver stability of future grids. There's going to be a project on hybrid metrology for battery materials. And there's going to be a project on grid data analytics. So data analytics for power systems. And these are very exciting projects that are going to start in the summer, and they're going to tackle some of the challenges that I've shown before. So that brings me to the end of this presentation. The EMN, as I said, was established to create a coordination amongst European NMIs to provide a coherent response to the energy transition, with the objective of identifying what are the measurement challenges for smart grids and developing roadmaps on how we can go about tackling those challenges and providing solution to the industry. And it's a document that we use to shape the direction of our R&D projects. So yeah, that's my overview. With this, I would like to thank, first of all, the project coordinators, because I just gave an illustration of what they do. But these are the people that actually coordinate the projects and lead the research activity. So thank to them, and thank you for listening.
Good morning, everyone. My name is Ilya Budovsky. I'm from the National Metrology Institute of Australia. And also for some years, I chaired the so-called energy efficiency focus group at Asia Pacific Metrology Program, which is a regional cluster of metrology institute. As Gert mentioned, our scope is quite broad. We look at the energy sector overall, but electricity is definitely part of it. So just to elaborate a little what we do in our relatively small activity, we have 3 objectives. We'd like to understand a little bit more about the industry needs when it comes to the energy sector. We want to showcase metrology to our stakeholders, and preferably to those who may not have heard of us before, not the ones with whom we have already very good relationship. And armed with this, we'd like to help our technical areas that are discharged through the technical committees to hopefully start new projects. And we do it through 4 main activities. We liaise with industry stakeholders. We try to maintain presence at key regional events, and preferably those that industry leaders attend, but sometimes it's the events where people may not even heard of NMIs, and they may not even heard of the the CIPM and the MOU and CMCs and things like that. And then we hold our own events, and we liaise across, and I think Stefano and Kurt in particular in participating in our events and collaborating with us. And then we liaise across the PMP to share the outcomes. Now, as we mentioned, the focus is quite broad. It goes to fuels, it goes to hydrogen, it goes to temperature, it goes to building efficiency. However, we've had several meetings on energy specifically. For example, this meeting on supporting renewables in renewable radioelectrical grids, and just late last year we had meetings with specific focus on supporting electrical energy sector. So some of our projects involve not only attendance and conference, but also actually going to stakeholders. So this is one of the projects where we brought a large contingent of emerging leaders from developing NMIs. And first we had our own event at a very large stakeholder conference, but then we visited a stakeholder, a large electricity generation plant, and talked to them about their strategy and talked to them about their priorities in energy. And then we sat down and developed for each developing economy, developing NMI that was represented. We heard about their stakeholder strategies, and we developed plans for each country as to how they will improve it and progress it. And now we are preparing a follow-up project just to see how the emerging leaders of this area, what they've learned. So in the remainder of the time, I will just very quickly share some of the learnings, and maybe in not a very systematic way, but just the way they come. So in Asia Pacific, the electricity generation, you can see the statistics, and there is some rapidly increasing share of renewable, and that includes and that includes the developing economies in the Asia Pacific region. So at the very high level, practically all Asia Pacific economies are committed to targets to reduce emission, and there's various high-level documents and high-level policies that are available in many countries that set certain targets. And here you can see some examples, and the presentations that I will share will have the links as well. So electrification is absolutely essential to achieving these targets. So when you look at electrical grids, measurements are done there always, in everywhere on the grid, with or without the participation of NMIs. So what we can do as metrology community, we can link these measurements to SI units where it's appropriate. We can refer them through measurement. We can increase reliability of these measurements through the use of measurement standards. And when it comes to metrological traceability, probably there is less to be done. We can be a little bit reactive because NMIs are known by those of our stakeholders that require metrological traceability. But when it comes to measurements really improving something, then such broad liaison it can be helpful. So the trends that we observe are not dissimilar to what has already been reported by Stefano in particular. So there's rapid integration of renewable energy sources. Asia Pacific, I can probably characterize as windy and vast. So there is a lot of onshore, but there's some offshore, there's developing offshore as well. So there is very large contribution of distributed generation. There's a lot of sun. In Australia, for example, in some states of Australia, on a windy and sunny day, 100% of energy is delivered from solar and wind. So there's real challenge of how to control it in such a way that it does not exceed the 100%, because that's absolutely not possible. Microgrids are developing, certainly very high, ultra high voltage DC transmission, and electrical vehicles as well, including wireless charging, particularly in China. And as we heard also, the grid is really embracing digital technology. So all of this requires measurement support. And here's probably some examples. So to support introduction of renewables into the grid, new classes or new types of devices are appearing, such as, for example, synchronous condensers, which are large rotating machines powered by renewable energy that help the grid. Harmonic filters, reactive power compensation, phase shifting transformers, all of that needs to be reliable, fit for purpose, and properly working. So that really benefits already and will benefit more in the future from input from NMIs with both utilities in skills in measurement. Another example is a fully digital smart substation in Thailand. I would say that digital substations are mostly, at least in Asia Pacific, mostly in transmission rather than distribution, because that's a smaller number of larger power that's been distributed. And this slide also presents challenges in achieving the interoperability of data and achieving the redundancies that exist there. And also, digital metering, digital meters and merging units are a key to these solutions, and they definitely require measurement support. Just going further, the very strong tendency that we observe is the broadening of the bandwidth of signals that are present in electrical lines, and also there's stability challenges in the forms of fluctuations are now penetrating through to not only are present at low voltage, which has been the case for a while, but they penetrate to distribution and transmission levels, and there they need to be, to support these networks, they need to be measured and understood. So one example of how an NMI reacts to this is a system that we developed in Australia to measure voltage, to calibrate voltage and current transducers with arbitrary waveforms that contains a fundamental and also harmonics up to 10 kilohertz. So we can generate, say, 100 volts, 50 hertz in Australia, plus we can also add 1 kilowatt of harmonics. Or we can generate 4 kiloamps of 50 hertz and add 1 kiloamp of harmonics of our choice, of our client's choice, at up to 10 kilohertz. And we can take the system off-site. We can take it on-site to the clients, so that, which is very important because downtime is, well, our engagement with the energy sector tells us one thing. There's just one plea. Please increase on-site capability. Please make sure or enable us not to bring very heavy equipment somewhere for calibration. So I think he already showed the diagram of how this works, but essentially what we do is we physically put in series a 50 hertz generator that generates 100 kV and the wideband generator that generates up to 1 kV of harmonics. And one, just to brag of one technical detail, when this happens is when we started this, we couldn't really get harmonics into the instrument under test. And that is because the 50 hertz transformer, it forms a divider with the measurement circuit. So the voltage at the measurement circuit is very much reduced. So what we've done is we put a capacitor here that shorts this arm of the divider at high frequency, but presents an acceptably low load for the transformer at low frequency. So I'm very happy with the solution. And now we can generate these composite signals. One other thing that I think Stefano also mentioned, all this, of course, leads to frequency variations. So at least in Australia, we have so-called frequency control auxiliary services. What this means is that when frequency changes, and that happens rather rapidly, as this graph from the Australian Energy Market Operator shows, the generator is paid to add very quickly, on demand, a very vast amount of energy into the system to stabilize the frequency. And meters and transformers are used to measure this and settle these transactions that involve megawatts ramped up in a matter of seconds or parts of a second. And this is a relatively new field, and of course it requires metrology. So just to end my snapshot of samples, electric cars, electric vehicles in Asia Pacific are progressing. This example is from Korea, and for those of you like me who can't interpret it, the green graph is the number of charging stations in Korea, and the black line is the increment per year. So the industry is growing, and one example here is that from Chris in Korea, where they have developed, and Chris is one of the NMIs that developed a system first to measure high DC current and DC power like that. And there's some others. I know China and also Australia will developing or have similar system. And I particularly like this slide that Hunkyu has provided with me that looks at the future, just where we will go. In particular, there is wireless charging, and I've already seen that in China. So where high frequency power is used to charge your car, and that of course necessitates some measurements as well. So my conclusion here is that we're really lucky. Measurements are everywhere, and evolving needs in the grid provide us with this opportunity, and I was just happy to give you some snapshots of that. So on that note, I'd like to say that my term as the chair of the Energy Efficiency Focus Group ended last year, and I'm very happy to introduce the new chair and the co-chair who is in this room. Please contact them. Jointly at the last meeting, we developed a future plan for the Energy Efficiency Group. So we are now implementing this plan, and I hope to see the activities continue and grow as the group goes. So thank you very much for this opportunity.
Hi, everyone. I'm Yang Pan from Shanghai Institute of Measurement and Testing Technology. We are responsible for the eastern part of China and for high voltage and high current calibration. In 2016, LIM led a project regard to the novel sensor calibration in digital substation, and we take part in that project. We are responsible for the electronics transformer calibration. So we have topic today, recent progress on the development of metrological traceability system for the electronic transformers in China. So the smart grid is the next generation of energy systems which have been updated with communication technology and connectivity to drive smart resource use, energy efficiency, and reduce the carbon footprint. Traditional energy grids are designed to transmit electricity from a large centralized power station to a wide network of homes and businesses in the area. With a decentralized model, a smart grid is designed to accept power from renewable resources, even if the centralized power plant is taken offline. Multiple alternative sources, including wind and solar, can supply the resources in a grid. So smart grid is resilient, efficient, and green, which is good for the consumers, the utility company, and the environment. In 2009, China officially launched the plan called Strong Smart Grid, and since then, China's smart grid construction has begun. In 2010, the Shanghai World Expo Smart Grid Comprehensive Demonstration Project served as a significant milestone in China's early smart grid development. The site incorporated electric vehicle charging and discharging stations, enabling bidirectional energy flow between electric vehicle and the grid, focused on renewable energy, storage, advanced automation, and consumer engagement, highlighting the potential for integrating advanced technologies to build more efficient, reliable, and sustainable urban energy system.
Dr. Pan, if I may shortly interrupt, we cannot hear you extremely well here in the main room. I don't know how it is online.
Excuse me?
But it would be nice. I don't know how close you are to your microphone.
My microphone? I'm sorry, can you hear me?
Yeah, we can hear you, but a bit from a distance, so.
All right.
It's pretty good online.
It's pretty good online, okay.
All right. So I'm sorry. So I cannot adjust my microphone. It's already the highest volume.
Yeah. Maybe speak somewhat louder, but this is already somewhat better.
Okay. Great. So a smart substation is typically implemented with a combination of smart primary high voltage equipment and networked secondary devices. Within this architecture, the electronic instrument transformer serves as a core component, providing accurate and reliable measurements of voltage and current. Based on the IC 61850 communication protocol, the functionalities such as the information sharing and interoperability among smart electric equipment are realized in smart substation. The adoption of electronic instrument transformers further optimize the smart substation, delivering benefits like reduced size and weight, improved performance, and increased flexibility. The introduction of electronic instrument transformers and merging units in digital substations is presenting new challenges for traditional metrology systems. The shift from analog to digital measurement challenges established traceability chains primarily based on analog signals. The key issues that metrology institutes are currently addressing includes the accurate calibration and the verification of digital output signals, ensuring precise time synchronization and characterizing the phase displacement introduced by the electronic instrument transformers and merging units, all of which impact the overall accuracy and the reliability of energy measurements in the evolving smart grid landscapes. So this diagram illustrates a typical digital substation architecture. During more than 10 years of operation in China, the prevalent approach for implementing IEC 61850-based digital substations utilizes traditional instrument transformers in conjunction with standalone merging units. While early implementations explored digital output electronic instrument transformers, this approach is currently not widely adopted. The instability of optical electronic transformers, which are susceptible to temperature or vibration, may be a primary contributing factor. The favored architecture relies on the standalone merging units to convert the analog signals from conventional instrument transformers into digital sampled values. So China has issued a series of calibration specifications to ensure accurate and reliable measurements. We have grouped the instrumentation used in digital substations into several categories, highlighting the different types of devices and their associated metrological requirements. First, we have non-conventional instrument transformers. These sensors represented here by the Rogowski coil LPCT, the capacitive divider. Next, there are electronic transformers with digital output. So examples of instruments in this category include FOCT, FOVT, and standalone merging unit. And then there are transformer test sets. These instruments provide a low voltage input as a reference channel and usually have a IEC 61850 SV input from electronic transformers or merging unit. So we have separate class for calibrators for the transformer test sets. These devices will often have both digital and analog output to calibrate electronic transformer test sets. So the reference calibration system is designed for both non-conventional and traditional instrument transformers. It comprises an active two-stage current transformer with a range from 0.1 ampere to 10 kiloampere. Reference voltage transformer with rated voltages from 10 kilovolt to 500,000 kilovolt. And we also have a set of non-inductive wideband current shunts and an inductive voltage divider. The wideband shunts and the IVD are selected to close match the input range of the sampling multimeter. Two key size 3458A sampling multimeters operating in DCV digitizing mode are used for simultaneous sampling of both the reference and the DUT with analog output. And a dual channel function generator provides a burst of triggering pulses to synchronize the two DMMs. In order to minimize performance variation between the two DMMs, an input switching controller is implemented to exchange the voltage inputs, thereby compensating for measurement errors. So the reference two-stage transformer aided with voltage follower is applied to minimize the inner magnetic flux, and the inner burden voltage of the secondary winding is removed. However, the capacitive error of the ratio winding needed to be evaluated, caused by the ground potential problem. This is realized by self-calibration with burden shunts. So when calibrating electronic instrument transformers, the output of the ECT or EVT are presented as a code of set of time coherent digital data streams. This is inherently necessitates a new reference system for accurate calibration. So in our approach, one of the DMMs is designated as the independent sampling reference. In order to ensure precise timing, a function generator receives electrical PPS signal derived from the MU and generates burst pulses to trigger the DMM for sampling. A fiber to SNAT converter then transfers the data packets from the MU to the computer's SNAT interface. Finally, a dedicated software platform has been developed to facilitate instrument control, packet capture, signal processing, and result display. So the synchronization sequence between MU function generator and also the DMM, including settings for them, are uniquely designed. For electronic transformer with a sampling rate of 4K, the MU multicasts the sampling values marked with number from 0 to 3,999, which is registered in the application data unit APDU of the SNAT frame according to the protocol of IEC 61850-9-2. So having received the electrical PPS from the MU, the pulse generator generates a burst of pulses with a preset number, which further triggers the DMM for digital sampling within the same second as the merging unit. So for the commercial electronic transformer test sets may incorporate functionality for testing both ECT and EVT. A ratio and a phase displacement source typically used for calibrating conventional transformer test set was employed to generate the reference current or voltage and differential current or voltage. The reference current or voltage is applied to the analog input of the electronic transformer test set. This reference signal with a superimposed differential current or voltage is digitized using the DMM. All sample data are then packetized according to the protocol and transmitted through the SNAT interface of the computer via SNAT to fiber conversion to the digital input of electronic transformer test set. So the DMM need to complete both sampling and packet transmission within 1 second time frame, limiting the utilization of all data collected within that second. Initially, the calibration system sampled for 12 cycles before packetizing and transmitting the data via the computer's SNAT ports. This requires that the transformer test set supported this functionality. The other problem is the process of packetizing and transmitting sampled values on the computer could not precisely control the frame dispersion. So in order to ensure simultaneous sampling by the DMM and the packet transmission, enabling real-time transmission of all data acquired within each second, we developed a synchronous data acquisition GPIP card and a protocol converter around 2020. So the primary function of the GPIP data acquisition card is to translate control commands into IEEE 488 compliant control instructions, enabling real-time control of the DMM via the GPIP interface. This ensures continuous sampling and data output while maintaining synchronous sampling. Secondly, the GPIP data acquisition card can convert the 3458A sampled values into messages conforming to the IEC 61850-9-2 protocol. The GPIP card utilizes an embedded design where control and data output are implemented using hardware logic circuits within FPGA, achieving a clock resolution better than 10 nanoseconds. So the GPIP card supports two sampling rates, 4K and 12.8K. So the protocol converter's function is to input and output data conforming to either the IEC 61850 protocol or the FT3 format, identifying its encoding method and baud rate, and convert it to TCP format for transmission to the computer. And additionally, the protocol converter can function as a synchronization signal generator, producing PPS or IRIG-B format synchronization signals, or receive input from these two synchronization signal format. Through the use of GPIP data acquisition card and the protocol converter, continuous and real-time packet reception and transmission operation can be performed on electronic instrument transformers and electronic instrument transformer calibrators, enabling data comparison within that second. So the amplitude and initial phase for the reference and the electronic transformer are processed using quasi-synchronous algorithm to compensate the non-integer period sampling due to the fluctuation of the power frequency. So improved quasi-synchronous algorithm with very high accuracy proposed in the practice. Simulation results show that the improved algorithm with 6 period iterations has a measurement error better than 10 to -10 for signals with great frequency deviation within 1 Hz for both amplitude and phase. No need for synchronization between the trigger and signal of the DUT. So each sample is taken by the integration over a time interval. The DMM effective averages the input signal during the aperture time. Amplitude error as well as a phase error can be introduced during the integration of a sinusoidal signal. This is compensated during the signal processing. So one problem is the DC input path is either through an amplifier or an additional resistive divider or directly goes to its ADC. It exhibits single pole roll-off, which is normally -3 dB down at the bandwidth point. This finally influences the amplitude and absolute phase. So according to the manual, the bandwidth vary from 30 kilohertz to 150 kilohertz, depending on the range selected. While this performance data is characteristic instead of a guaranteed specification, it needs to be measured in order to compensate accurately. However, the direct bandwidth measurement at frequency up to 150 kilohertz is not possible because the maximum sampling rate is limited to 100 K in DCP mode. So this is a downsampling technique by sampling in different periods and map sample to the corresponding instance within 1 period, and have been successfully in obtaining the bandwidth combined with the improved quasi-synchronous algorithm. So the strategy for frequency amplitude digitizing is shown in this table. So the downsampling coefficient is introduced to define the extent of downsampling. As the frequency increases, the number of cycles used for the downsampling coefficient also increases. Consequently, the integration time That is, the capture time must be reduced accordingly. So, this picture is the test result of amplitude frequency characteristic for different range. 2 DMMs are tested simultaneously. The bandwidth of DM input pulse is range dependent and also showed as slightly instrument dependent. If the bandwidth is defined as the frequency at which the amplitude frequency response is attenuated to -3 dB, then according to the manual, the input bandwidth of 1 volt range and 10 volt range are typically both the same 150 kilohertz, while the test results show that for 10 volt range, the input bandwidth is tested to be lower than 120 kilohertz. So research have been carried out in considering its actual internal physical construction circuit, which is equivalent to be a second-order low-pass filter composed of 2 5 kilo ohm resistor to 82 picofarad capacitor. Both first-order and second-order least mean square feet are performed on the 1 volt range and 10 volt range according to the test curve, respectively. Results show that both of fitting curves agree well with the measured frequency amplitude curve for relative deviation within 50 ppm up to 1 kilohertz. However, fitting curve for high frequency is proved to give rise to large uncertainties when it comes to the absolute phase measurements. So this leads to the speculation that the approximation using both models to calculate the phase shift may introduce errors. The actual model for the input pulse of DMM may be much more complicated. So the other method can be used to calculate the time delay introduced by the bandwidth by changing aperture time of the DMM, taking advantage of the fact that the integral of this sinusoid wave has a zero mean value over an integral number of cycles. So aperture time methods have been proven to be effective at high frequencies. However, when the frequency decreases, the resolution of integral value in the zero crossing region of the sine wave used to find the minimum becomes extremely small due to the very small proportion of the time delay relative to the entire period. The latency caused by bandwidth limit is hard to be determined at frequencies below 10 kilohertz. So this problem is solved by shifting the phase of the trigger pulse output from the synchronous dual channel signal generated by 90 degrees. In this way, the integration interval is located in the peak area of the negative half cycle of the sinusoid wave, and the symmetry of the positive and the negative half cycle of the sinusoid wave is used to find the zero crossing of the integral region instead of finding the minimum value proposed in the previous method. So the optimized method greatly improves the sensitivity and extends the lower limit of the measurement frequency to 50 Hertz. So the final test result for 2 DMMs is range dependent and also instrument dependent. So it is worth noting that all digital measurements are ultimately traceable back to analog quantities. In the case of voltage transformers, most national metrology institutes still perform traceability through measuring the voltage coefficient of compressed gas capacitors. At this point, I would like to briefly mention the advancements China has made in this field. So eccentricity of the electrode alignment induced by electrode position and geometry variation is considered to be the main contribution to the voltage dependence of such kind of gas compressed high voltage standard capacitor. Investigation had been carried out in this field, including double frequency method, DC biasing method, tilting method, and also the voltage doubling method. So among all these test methods, the voltage doubling method offers a key advantage. So the simultaneous determination of both the voltage coefficient of capacitance and the dissipation factor. Furthermore, the test is performed under actual power frequency operating conditions without requiring any specific preconditions. The voltage doubling method was initially proposed in 1987. So early implementations faced challenges operating above 50 kilovolt due to harmonic content. However, an improved voltage doubling method featuring a ground floating bridge with remote transmission for real-time monitoring of the 2-to-1 operating voltages has been successfully implemented on a new calibration platform up to 400 kilovolt in SIMTT, enabling accurate assessment of both the voltage dependence of capacitance and dissipation with uncertainty around 5 ppm. So, this is the final uncertainty evaluation for the current transformer. The calibration platform applies for conventional current transformer and also ECT with analog output and also with digital output. So this is for the voltage transformer, both for conventional voltage transformer and also the non-conventional voltage transformer and also with digital output. So summary. So the real-time calibrate system for both non-conventional instrument transformers and electronic transformers with digital output is realized. So the calibration system, including the channel switching measurement techniques and timing control the trigger sequence for achieving synchronization between the DMM and the PPS, which is aligned with the timestamp of the SV packet from the MU. The optimized uptime method proposed greatly improves the phase characteristic measurement sensitivity and extends the low frequency limit to 50 Hertz. So the voltage doubling method enables determination of voltage dependence for both capacitance and dissipation factor of compressed gas capacitors under operating conditions. All right. Okay. Thank you for your attention.
Thank you very much, Gerd. So yes, my name is Deborah Ritzmann. I'm a scientist at NPL, the UK National Metrology Institute. I focus on research and development for power systems measurement challenges. And I very much want to highlight my collaborators, Paul Wright, Peter Davis, Stefano Lodetti. They've all contributed to the work that you're going to see. Today, my talk is about power quality and grid disturbances. So it's going to be, how do we move forward? There we go. It's going to be quite broad. Hopefully you'll get a nice cross-section of the different issues that we're working on. We will definitely touch on things that we've heard before this morning. But we'll start off with what is power quality? What are the traditional metrics? And then looking at, well, how is all of this changing? How do we manage power quality going forward, given that we're going to have converter-dominated grids? And then there's kind of 4 topics that I'm going to cover. One of them are the new disturbances in the frequency range up to 150 kilohertz, also called the supraharmonics. And I'll spend quite a bit of time on those. But I'll also touch on that new phenomenon of subsynchronous oscillations, as well as grid impedance measurement, inertia, and power frequency. But I'll explain how all of this is somehow interrelated. So firstly, what is power quality? Well, if we go to the IEC kind of vocabulary, it tells you that it's the characteristics of the electric current, voltage, and frequency. And we try to keep them within certain reference parameters. And it's also very much related to making sure that the electricity or the power that's being produced is compatible with what the loads would like to consume in order to function properly. So in an ideal world, this is what power should look like. So you've got, for example, a very sinusoidal 230 volt waveform, 50 hertz frequency, and in Europe is the reference, or in other places 60 hertz. But in reality, it's never like that. Usually you have some kind of distortion, you have transients, the magnitude of your voltage, for example, varies. That's okay, as long as you don't go outside of certain limits. If you have excessive deviations, it can really cause problems. So it causes additional losses, it can damage equipment, it can malfunction, and also even worst case, it can cause grid instability. So that's why managing power quality is really important. Now, traditionally, or still today, really, you can go to the 61000-4-30 standards, and that will give you normative methods for a range of power quality phenomena. So including the frequency itself, for example, harmonics are a very big topic, also voltage Gibbs wells. I won't mention all of them, but this is kind of the set of power quality parameters where we've got normative methods, they're well-defined, everybody uses the same methods, everything's comparable, and then they're implemented by manufacturers on power quality instruments, and then they use them to check whether in their grids everything is compliant with the limits, and if there's a problem, they will try to understand where it comes from in order to rectify it. This is to some extent where the standardization is really important, because, for example, if you identify that there are harmonics, you need to, and you identify who the source is and a solution for it, somebody has to pay for it. So whether the utility pays or whether the customer pays, that's a very material question. So making sure that everybody has the same reliable methods and consistent methods becomes very important in such questions. But everything's changing, as we've already heard today. We're moving towards a grid that's going to be much more dominated by, or in many places, by converter connected technologies on the supply side, but also on the demand side. And today I'd like to highlight kind of two big kind of changes that are as a consequence really that affect power quality. So one is we've got new disturbances that are being introduced into the grid, but also the susceptibility or the sensitivity of the grid to those disturbances is changing. And in combination, that leads to new power quality challenges, and the methods that I just showed that are existing are not fit for purpose to manage all of these kind of novel effects. Now, I mentioned new disturbances. Today, I'm going to focus on kind of especially the disturbances in the 2 kilohertz to 150 kilohertz range. We've done a lot of work on this at NPL in collaboration with other European institutions, and they are more or less steady state type of emissions. So they can also have some kind of temporary nature, but they tend to be associated with the operation of certain equipment, especially converters with high switching frequencies. And the manufacturers to some extent have exploited this frequency range because in the harmonic range, there was a lot of restrictions. It's been well regulated. So, and also there was some efficiency gains in going up in frequency, but the emissions in that frequency range have been increasing. And there are documented problems with interference cases with those emissions in that frequency range. You can look up the Senelec reports, for example, and their stories about hair dryers, washing machines that don't function properly or that magically turn on and off. So it's a real concern, also especially for power line communications. So a lot of smart meters, they will send communication signals in this frequency range, and that communication can also be affected. I'm also going to touch on another type of disturbance that we're seeing increasingly in the grid. They are of a more transient nature, but they also affect power quality in the sense that they can basically push the voltage waveform outside of the parameters that it should be in order to ensure a good functionality of the grid. They also originate from, or there's a new type of these oscillations that originate also in particularly from power electronic converters. So I'm going to touch on that as well. So we've got two new types of disturbances, but then we also have what here today I call it a higher susceptibility or maybe a sensitivity to those disturbances. So you can have an emission into the grid, but the impact on the grid depends on how long and how big that disturbance is going to be. And that depends on how strong the grid is. So a lot of people talk about grid strength, and if you have a lot of synchronous machines, in general, that is a strong grid because they inherently will counteract most types of disturbances. They provide a kind of voltage stiffness, and that's because they have this stored energy. The big synchronous machines, we already heard about inertia this morning. So if there's a fault, they can inject quite a lot of power. They can inject and maintain a lot of current, which means that the voltage, it prevents the voltage from collapsing. But as the synchronous machines are going away, the grid is becoming weaker because most of the converters that are existing today, they're not grid forming. We heard Stefano talk about a new project to look at new types of converters, but most existing ones, they've got limited current capacity and their control systems are not designed to provide this voltage stiffness. They actually look to the synchronous machines to provide that voltage stiffness. So not only do we have new disturbances, potentially a higher number of disturbances, we've also got less inertia, we've got less what we call short circuit levels, so less fault current. We also have less damping, which is related to the extent to which those oscillations that I mentioned actually persist in the grid. So really, I think we probably need to not only look at the power quality side of capturing disturbances, but we also need to start to look at things maybe a bit more holistically or in an interconnected way related to this grid strength characterization. On the topic of grid strength, if we look at the short circuit level and the damping, it's worth to note that in terms of the actual property in the grid itself, that's very much related to the grid impedance. So I'm going to also touch on some of the measurement challenges associated with that. So yeah, just to kind of summarize the picture, there's new disturbances and network operators need to be able to measure them and characterize them and monitor them to make sure that the existing level doesn't surpass the compliance limits. So we've got the high frequency new disturbances, the subsynchronous oscillations, but also frequency measurements are becoming a lot more important because of this inertia. We can get worse and we can get also more frequency deviations depending on what's happening in the grid. But then the other side of it we also need to characterize this grid strength. So what is the impact of those of such disturbances potentially going to be in the grid? I'm very conscious that I'm crossing over a bit into another talk. Probably that's going to happen today. So those concepts, the grid impedance and the inertia, they're very much related to grid stability. So I'm not inventing anything new, but just highlighting really that we need to consider them in combination. So first of all, yeah, let's talk a bit more about the 200 to 150 kilohertz conductor disturbances, also known as supraharmonics, but they're not necessarily harmonics. So they're not necessarily only multiples of the 50 hertz. They can also be at other frequencies. Firstly, what's the status of standardization? Why is this important? So normally there's or especially for harmonics, let's say at up to 2 kilohertz, there is what we call an electromagnetic compatibility framework. And that's makes sure that there's no interference. You've got your compatibility levels, and that's kind of the maximum acceptable level of disturbance in the grid. And then you've got immunity levels. So all the appliances, everybody who connects to the grid has to tolerate that level of disturbances, at least. Usually the immunity level is higher. And then you've got emission limits, and they limit what can actually be injected into the grid by individual appliances. And this kind of this framework usually makes sure that it's really good at making sure that there's no interference. But you need to enforce it. So you need to also check whether in reality in the grid, everybody is sticking to what they're supposed to and make sure that there's no problem. So you need a measurement method that allows you to do this monitoring. And I've highlighted kind of the parts in red where the standardization and the EMC framework in this frequency range is not quite complete yet. So we've got compatibility levels, which have been defined up to 150 kilohertz. We've got immunity levels, emission limits. We have some, but they're only really for specific appliances, for example, lighting, induction cookers, but especially for things like EV chargers, which are very big emitters, and we're going to hear more about that today. It's getting there, but it's still in progress. And the grid measurement method, which I'm going to talk more about, there's a new proposal on the table in the 61000-4-30 standard. And that's actually been published for comments last year. So the next edition should be out in the next 1 or 2 years. Yeah, so at MPL, we coordinated the Super EMI research project, which ran from 2019 to 2022. And many of the, or a few of the collaborators are also in the room today. And we worked really quite closely with the standardization community on looking at how can you standardize these types of measurements? How will utilities do these types of measurements in the future? What kind of measurement method could be suitable to include in the standard? So the grid measurement method, there were different types of candidate methods that were under discussion, but really the key driver for what the grid measurement method should look like comes from the compatibility levels, because you want to be able to compare the result of your measurement method with the compatibility level to check whether the disturbance levels in the grid are compliant. And so the way that the framework looks like at the moment, if you look at the compatibility levels on the right, from 2 kilohertz to 9 kilohertz, the compatibility level is defined as an RMS value. And that RMS value, the computation of that is defined in the 61000-4-30 Annex B standard, so the standard for the harmonics measurement methods. And it's quite similar to the measurement methods for harmonics. So it's something relatively familiar, I think, for the power quality community. Once you go from 9 to 150 kilohertz, the compatibility level is defined in terms of the CISPA-16 quasi-peak value. So this comes from the radio frequency standards. And the reason is that there are some existing emission limits, and there's also a measurement method for individual appliances in the laboratory where we characterize emissions using the method that's in CISPA-16. I say we, I think it's not necessarily the power quality community, because the quasi-peak really it was designed to protect radio transmission signals. So it basically is a weighting of the rate of repetition of an emission. So it looks at the amplitude and it looks at how often does it repeat, and the more repetition you have, the higher your quasi-peak, but it will always be lower than your absolute peak. And it was designed to characterize kind of this annoyance that you can get when you're listening to the radio effectively and there's an interference. So this isn't something that's been designed for superharmonics in the grid. But in order to have a consistency and comparability in the EMC framework, this is kind of the most likely method that's going to be adapted. And it's been proposed in the public draft of the new standard or edition of the standard. So yeah, at MPL, as I said, we had this research project where we've developed an on-site measurement system. And we've implemented this CISPA-16 method, and we've taken that system out to do some field measurements, really with the objective of starting to get an idea of what are the emission levels or the disturbance levels that are currently existing in the grid, because it's not something that any of the utilities are really monitoring consistently yet. And also to trial this measurement system to get experiences, to be able to provide guidance to instrument manufacturers and to utilities for how such type of power quality surveys in the future should be done, or what could be potential problems. And we actually measured in total at 3 different locations. And at all the locations, there were at least 2, or there were rapid or ultra-rapid 120 kilowatt chargers. At one location, there were 4, and then at the other locations, there were 2. And at all of the locations, there were also other loads. So it wasn't necessarily only the EV chargers that were impacting what's happening on the network. And so I'm just going to show some sample results. There's actually a conference paper that you can look up to read a bit more about it. But on the left-hand side, for example, what you can see is the spectrum that's resulted using the CISPA-16 quasi-peak value from one of the locations. And you can see these peaks, and they are associated with what we believe is the switching frequency of those EV chargers. We think it's usually the first one, around 22.5 kilohertz in this case, and then you can see the harmonics of this switching frequency. And with the quasi-peak, traditionally, the way it originally was defined is that you take the maximum value over a certain time period. And in this case, we actually found that one of the frequencies, the one in the middle around I think 67 kilohertz, briefly exceeded the compatibility level. So this wasn't for a long time. If you look at the plot in the middle, it actually shows this frequency component over time. And you can see that there's kind of a peak in the middle of the plot where the amplitude of the frequency component briefly increased and then it came back down. And it's quite interesting because we also plotted another, around 17 kilohertz frequency or 18 kilohertz frequency component. And you can see that they don't necessarily have the same kind of time progression. So in the second kind of half of the plot, the EV current or the charging current decreases. And you can see that the 67 kilohertz frequency component stays relatively constant, while the one around 18 kilohertz has a lot more variation. And then on the right-hand side, you can see a spectrogram where you can kind of see the kind of broad range of emissions that are occurring across the frequency range, several kind of narrowband emissions, which are the horizontal line that sort of persist throughout the time period. But there are also these like two vertical lines, which are sort of quite distinct time periods where there was a broadband emission. And it just goes to show that as you've got more of those devices that have emissions in that frequency range, we're starting to get quite a complex picture potentially or pattern of what's happening. And it also goes to show that the importance or the likely importance of monitoring those types of emissions or disturbances in the future. So just to conclude on the supraharmonics, what's the outlook? So thinking about the future that we're talking about today, we're expecting the completion of the standards framework in the next few years. Probably the CISPR-16 method is going to stay. It's probably going to be a new thing for everybody to get used to. And these measurements will become more and more important for manufacturers and for utilities to do on a regular basis. There are still some open challenges to better understand how those types of disturbances behave in the power network. So propagation, especially, so everything we're talking about until now is in the low voltage network, all the measurements, but those disturbances may be injected at the medium voltage level, or they may propagate from the low voltage network. And there are still open questions about that, resonance, and also how all of this relates to the impedance. And then again, we talked about AC networks, but there are also DC grids for which we also will have to consider those disturbances. So now I'll touch on some of the other disturbances, which I think are also interesting to bear in mind, thinking about what's coming ahead. So let's start with the subsynchronous oscillations. They are basically, they're not an entirely new phenomenon. There used to be, or there are oscillations associated with how synchronous machines work. But the power electronic converters are introducing a new type of subsynchronous oscillation. And for example, in the UK, in the GB power system, which is a slide from a webinar from our system operator here, you can see an example of, so 3-4 years ago in 21, they saw a significant oscillation. So you can see it was on the 400 kilovolt network. And the amplitude variation in the voltage for a short period of time was around plus or minus 30 to 40, 50 kilovolts even. At the time when it happened, it was quite surprising and it was quite concerning, and it did cause some assets in the grid to activate their protection systems and disconnect. And so since then, really everybody's been on high alert to try to understand those types of oscillations, where they might potentially come from. But there's still some open questions as to how they can or should be detected and measured in the future. Obviously, they're visible using today's systems. Mostly people tend to use phasor measurement units in order to detect them, or they notice them through the amplitude variations. But if we think about a phasor measurement unit, it's designed to measure the fundamental frequency phasor. So it's usually at 50 or 60 hertz. And actually it's got filters, internal filters, that try to suppress other frequencies. So while we can still see some of those oscillations in the phasor magnitude, there's a question as to whether those oscillations are being reflected properly by those types of instruments or the way that they work nowadays. And so here on the right-hand side, you can see some work which Stefano, who you've heard from today, has been leading our team on. And it really shows some initial analysis looking at, well, if you've got, for example, a 45 Hertz frequency component, which would cause a subsynchronous oscillation, then potentially some of the PMU algorithms might not actually fully reflect that frequency component. And therefore, potentially, these oscillations that are being observed, they're causing concern, but maybe they're also not yet being fully characterized. So from our perspective, we think there are some open questions, potentially also the reporting rate needs to be considered. And for sure, there's a lack of standardization as to how you implement those types of detectors. And then I did touch upon grid impedance. Grid impedance is highly important both for supraharmonics, so in the 2 to 150 kilohertz frequency range, but also when we go and think about those subsynchronous oscillations. So the extent to which they persist very much depends on the damping. If we have a lot of damping, usually the oscillations will go away quite quickly on their own. So for network operators, it's becoming, if they want to maybe try to prevent some of these transients in the first place, rather than waiting for it to happen, they need to, in advance, understand what's the sensitivity of the system to react in such a way. And that's where the grid impedance becomes an important factor. In principle, measuring grid impedance is relatively simple. In principle, I would say you basically need to measure the change in voltage divided by the change in current in simplified terms. And for low voltage networks, it's there are mature commercial solutions going into the kilohertz or hundreds of kilohertz. So I would say it's something that's quite well established, although not necessarily standardized. But once we start to go to medium and high voltage networks, which is where especially these transient oscillations occur, there are a lot of questions because in order to measure the impedance, you need a disturbance, you need a perturbation, and then you measure the response. So there's a question as to, well, how do you generate this type of perturbation? But from the measurement point of view, you need to be able to, you need your instrument transformers to be characterized. You need to know the amplitude error, you need to know the phase angle, and you need to know that across the frequency range. And because here for the impedance, we're talking about the difference measurement, it becomes even more important than for some other applications, because even a relatively small ratio error, if you're measuring a small difference in your voltage, let's say 5%, then suddenly a 1% amplitude error is already a 20% error in your measurement, potentially, in simple terms. So we're going to hear a bit more about characterization of the frequency response of instrument transformers from Mario. And yeah, it's a highly important topic, also that links into power quality phenomena. And then the final topic that I'm going to touch on is inertia and power frequency measurement. So what's inertia? As I mentioned, it's this kinetic energy that's stored in the synchronous machines. And if you have a disturbance in the frequency, it's usually because there's an imbalance in the power supply of the electric power system. And those synchronous machines release this kinetic energy, and thereby they slow down the drop in frequency. So if you have a lot of synchronous machines, you've got high inertia, and then your rate of change of frequency is low. But because we're replacing a lot of synchronous machines with power electronic converters, we've got decreasing inertia, and there's a higher risk of any type of frequency deviation to be, for the frequency to fall faster, and it will also, for that reason, likely take longer to recover. So frequency deviations or frequency excursions are becoming a larger concern for that reason. So what you're looking at here is basically so on the plot, you see the frequency, you see 3 frequency measurements that we've taken using our instruments from NPL, and we took those frequency measurements in 3 different locations in the GB grid. So one was in the north, one was in the south, kind of above the Scottish border, and then one was in the south, very much in the south, so in the kind of London, Teddington area. And then there was a disturbance on the network. So there's an interconnector between Great Britain and France, and this interconnector suddenly tripped, it disconnected. So a lot of power was suddenly gone, 1 gigawatt, and that caused this frequency disturbance. And what you can see is actually, maybe counterintuitively, the frequency measurements are different across those 3 locations. You can basically see some oscillatory behavior. You can see one very large kind of dip in the orange Teddington frequency line. That's because there's a phase jump that's associated with this type of disturbance. And one of the questions that in this project we were trying to answer is, well, if we want to characterize the inertial response of the system, then really the frequency measurement should tell us what it is. So how do we get a frequency measurement from these 3 measurements that's reflective of this inertial response? And so this really is just to show that frequency measurement isn't necessarily a straightforward thing to do, depending on the dynamic situation that the power system is in. And so we've been doing some work basically to look at, well, how can we remove some of those transient effects to obtain a frequency trajectory that is representative of this inertial response in the power system. And we've been providing that as a reference measurement to the transmission system operator in the UK. And they can use that in order to make a comparison with the frequency response that's predicted when they have an inertia measurement, maybe an inertia value that they've calculated, or in this case, also an inertia measurement that comes from a new commercial system. So in terms of validating new systems that are coming onto the market, I think metrologists have also a large role to play here. So yeah, just to summarize the talk, I've mentioned some new measurement challenges that relate to the power quality in converter-dominated power grids. We've talked about new disturbances that we're seeing and an increasing occurrence of disturbances, and also the importance of characterizing the grid strength and some of the measurement challenges associated with that, grid impedance, grid inertia, which are linked to the grid stability. And yeah, from our perspective, the role of metrology is to develop new methods, metrics, and instrumentation, and to provide guidance to industry, and to make sure that there's comparability, to enable standardization, and also to enable the verification of new systems. We've talked about or heard about the industry being conservative. So for them, having reliability in any new kind of methods, metrics, and instrumentation that they're using, and having that trust and confidence is highly important. Okay. That was it. That was my talk. So thank you very much for listening.
Good evening, ladies and gentlemen. I am Mario Luiso, and I am a professor of electrical and electronic measurements at University of Campania, Luigi Vanvitelli, Italy. First of all, I would like to thank Gert for having invited me today, and people from BIPM for hosting me today. I am very honored to be here today. In this presentation, I will talk about, among the other things, of the ADMIT project, a project focused on the characterization of instrument transformers up to 150 kHz that got funded from Euramet and the European Union. Let's spend just 30 seconds on terminology. What is an instrument transformer? An instrument transformer is a transformer intended to transmit an information signal to measuring instruments. The term instrument transformer encompasses both voltage and current transformers. But the terms instrument transformers, voltage transformers, current transformers are generic terms. They do not refer to a specific technology. So inductive instrument transformers and low power instrument transformers are both instrument transformers. And voltage and current sensors that are intended for power system application are instrument transformers. The history of instrument transformer calibration probably begins in the 30s, so almost 100 years ago, but at that time, almost all were sine waves. So, but today is no more like that time. So let's concentrate on more recent issues. So instrument transformers for the measurement of harmonics and in general, distorted signals. An obvious sentence for today is voltages and currents of power systems are distorted. But a less obvious sentence still today is VTs and CTs should be tested with distorted waveforms. Distorted waveforms in the sense that they should be representative of actual power system waveforms. One of the first examples of testing instrument transformers for harmonic measurement is about of 1985 from people from University of Canterbury in New Zealand. They were doing measurements at high voltage level, and they noticed that the measurement of that harmonics with inductive instrument transformers were distorted. So they thought to characterize the instrument transformers with a new kind of setup able to generate harmonics at high voltage level. It is interesting to read the conclusion of the paper now 40 years ago. Of particular importance is the influence of the fundamental voltage magnitude upon the frequency response obtained. And also, further, the need for the provision of a suitable harmonic source capable of supplying a full range of harmonics at full system voltage has been recognized. So these findings of 1985, about 40 years ago. But we have to wait until about 2009, colleagues from University of Palermo that maybe for the first time gave in literature an example of the comparison among the two approaches for the measurement of the frequency response of an instrument transformers. So with sine waves, having full ranges, but variable frequencies, and the distorted waveforms. So waveforms composed of a fundamental tone having the rated amplitude and one single sweeping harmonic component at 10% amplitude and different frequency. And finally, in these two papers of 2019, one from my group and the other from colleagues from Politecnico di Milano, they find the cause of nonlinearity of inductive transformers and suitable compensation methods to reduce the nonlinearity of such inductive transformers. So, supposed to supply the instrument transformer with a distorted waveform, fundamental tone plus harmonic tones. The phasor of an harmonic component at the secondary side of the instrument transformer is essentially the sum of two contributions. The first is the phasor of the same harmonic at the primary side of the transformer multiplied by the complex gain of the instrument transformer at the harmonic frequency. And the second is an error component that is largely dependent on the fundamental component at the primary side. This error term can be measured by supplying the instrument transformer with distorted waveforms and can be used to compensate the nonlinear behavior of the inductive transformer. But should we use distorted waveform for every instrument transformer? Well, literature essentially discusses the nonlinearity for inductive instrument transformer, and it is clearly shown that they have to be tested with distorted waveforms. Instead, in literature, low power instrument transformer, essentially dividers and Rogowski coils, are mainly treated as linear devices. But in my opinion, attention should be paid to the insulation material that can modify the behavior of the instrument transformer. Generally speaking, low-power instrument transformers are quite recent, and literature, about 10, 15 years, provides less information with respect to the inductive instrument transformers. But what about standards? We essentially have, related to this topic, two sets of standards. The first set regards the voltage characteristics in electrical systems, limits of disturbances, measurement of disturbances, characterization of power quality instruments, standards on phasor measurement units. These, all these standards do not consider the instrument transformers. On the other side, we have the standards on instrument transformer, mainly the family standard 61869 from the IEC. The recent standard 61869-1 edition 2 gives accuracy requirements up to 500 kilohertz, but only requirements without giving indication on how to test these instrument transformers up to so high frequency. In general, the standard family gives indication on accuracy verification only at 50-60 Hertz, and says to verify at higher frequency, but with signals with reduced amplitudes. So, summarizing, they do not consider power quality. So we are in the strange situation. We can buy on the market a compliant instrument for power quality measurement, a compliant instrument transformer, and if we join these two devices, probably we will not get the performance we will expect. So, joking on this topic, it is like Homer Simpson that wants to build a puzzle starting from two sets of pieces. A set that contains compliant power quality instruments, another set that contains compliant instrument transformer. How to join a compliant instrument transformer and a compliant PQ instrument? Unfortunately, basic solutions are not allowed. But coming to more serious technical issues, let's now see how in recent years this topic have been faced in European metrology research project. Mainly two research projects, IT4PQ and ADMIT, had as main focus the characterization of instrument transformers. IT4PQ ended in 2023 and wanted to characterize instrument transformers up to 9 kilohertz. And ADMIT project is still in progress. It will end next year, May next year. And it wants to characterize instrument transformers up to 150 kilohertz. Obviously, also other projects face topics similar to this, but even not as their main focus. Projects like Future Grid 1 and 2, Smart Grid 2, MyRails, DC Grids, but also other projects. So in the rest of this presentation, I will talk about the main results of IT4PQ and the first result of ADMIT project. The aim of IT4PQ project was to develop the metrological framework in terms of methods, systems, and procedures for the traceable characterization of instrument transformers for power quality measurements. And the focus was on distribution grids, so 36 kilovolts and 2 kiloamps, with disturbance frequency up to 9 kilohertz. the data and the findings were transmitted to the ICTC 38 committee that was the chief stakeholder for this project. So we started with the selection of the disturbances that were used for the characterization of IT performance verification. So stationary disturbances like frequency and amplitude variations, harmonics and interharmonics, but also oscillatory transient and, let me say, dynamic phenomena like amplitude and phase modulation. All these phenomena have to be superimposed to a rated voltage and frequency fundamental component. And moreover, performance indexes that quantified the performance of the instrument transformer in the measurement of a particular phenomena were defined, both for stationary phenomena as well as transient phenomena. Various reference setups were built during this project. I cite just 3 setups, one for voltage transformer characterization at INRIM. It makes use of an arbitrary waveform generation, a medium voltage amplifier up to 30 kilovolt, a reference divider homemade by colleagues of INRIM, a comparator made by National Instruments Data Acquisition Board ranging from 500 millivolt up to 400 volt input range. And it is able to generate all the cited disturbances up to 9 kilohertz. Another setup developed at PTB is able to generate up to 2 kiloamps and 9 kilohertz. The generation part is made by an arbitrary waveform generator, a power amplifier, and a step-down high current transformer to generate the high current waveform. The uncertainty is similar to that reached with the INRIM system, about 200 ppm for the ratio, and about 300 microradians for the phase. Another setup was developed at TÜBİTAK for the characterization of 3-phase combined voltage and current transformers. It is able to reach 36 kilovolts and 2 kiloamps up to 9 kilohertz. Uncertainties are 500 ppm and 500 microradians up to 9 kilohertz. All these reference generation and measurement setup were used to characterize a number of commercial devices, number in terms of various input rated voltage, outdoor or indoor application, or even different technology. I don't spend too much time on commenting these results since the time runs fast. Another important aspect defined in IT4PQ project is the definition of an aggregated performance index, something like a PQ accuracy class, so an extension of the classical definition of accuracy class of the instrument transformers, but for power quality measurements. Another interesting thing was the testing of several types of instrument transformers against influence factor like temperature, adjacent phases, and the proximity, the position of the cables inside a Rogowski coil, and the vibration. Summarizing, the main results of IT4PQ were the development of reference setup for voltage transformer and current transformer calibration up to 36 kilovolts, 2 kiloamps, 9 kilohertz, the definition of a new PQ accuracy classes, the verification of the influence factors on the performance of instrument transformers when measuring harmonics. All the outcomes have been provided to the working group 47 of the ICTC 38 that established the working groups, task forces to include these findings in future versions of standards. Now let's talk about briefly about ADMIT project. It started in 2023 and it will end in 2026 next year in May. Why ADMIT project? ICTC 38 explicitly asked for research to address standardization up to 150 kilohertz. From measurement and industrial point of view, what are the needs? Switching power converters nowadays can be directly connected to medium voltage, and they can have a switching frequency in the order of tens of kilohertz, power in the orders of tens of kilowatt, and voltage in the order of tens of kilovolts. So the switching frequency behavior originates harmonics of the switching fundamental tone up to hundreds of kilohertz. They are not harmonics of the 50 hertz. This is why I don't like very much the term supra harmonics, because it is quite confusing. They are harmonics, but not harmonics of the 50 hertz. They are harmonics of the tones around the switching frequency. In fact, these tones typically are not synchronous with the power frequency. They interfere with the power line communication, causing failure of grid automation and meter reading. They increase losses, so more economical losses. They can couple with the control system of inverter, causing possible local blackouts. So to avoid disasters, it is of vital importance to measure emissions at least up to 150 kilohertz, also in medium voltage grids. The ADMIT project has 13 partners, 7 national metrology institutes, 3 universities, 1 research centers, and 2 companies. The objectives to identify performance requirements for instrument transformers up to 150 kilohertz, to establish suitable parameters for the definition of accuracy of voltage and current transformers up to 150 kilohertz, to produce test setup for the generation of test voltage and test current up to 36 kilovolts and 2 kiloamps for AC and DC grids with reduced components up to 150 kilohertz, to develop reference measuring system for AC and DC grid up to 36 kilovolts, 2 kiloamps, 150 kilohertz. And to provide the data methods, guideline, and recommendation to the standardization committee. Essentially, the objective of ADMIT project is to go beyond the state of the art that currently is, I can say, represented by the IT4 PQ project. It wants to extend the findings of IT4 PQ project for DC grid and up to 150 kilohertz. So the first results of ADMIT projects are focused essentially on the techniques for the generation of high voltages and high currents, but with reduced components up to 150 kilohertz. Differently from IT4 PQ project, here it is difficult to reach with one single generator at the same time high voltage and high frequency. So the various partners concentrated on the use of 2 different generators to reach this kind of performance. So at LNE, used two AC grounded voltage generator connected in parallel with suitable blocking elements to avoid that they can destroy each other. So the first test shown that it is able up to now to reach 15 kilovolts plus 500 volts up to 150 kilohertz. At the University of Campania, with support of INRIM, we have developed an architecture for the generation of medium voltage, but with 150 kilohertz component, using two series connected generator. Essentially, it is based on a step-up transformer with a high-frequency amplifier, but with the use of a shunt, let me say shunt capacitor put in parallel at the secondary side of the step-up transformer in order to reduce the voltage drop on the secondary side of the transformer. It is something like Ilya shown this morning. And also the measurement of the generated voltage was split into the fundamental tone was measured with a commercial divider. Instead, the high frequency component were measured with the homemade divider that has a high pass behavior. So it is able to measure just the high frequency component from 9 kilohertz up to 150 kilohertz. This setup was used to test, for instance, a commercial medium voltage inductive transformer. In these two pictures, we can see on the left the spectrum of the input of the inductive transformer, and on the right the output. We can see that we supply almost with the pure tone at 100 kilohertz, but at the output we don't have a pure tone at 100 kilohertz. So this is a proof of the non-linearity of inductive voltage transformer even at so high frequency value. At FFII, developed two series connected generator, but with a fundamental component at 0 hertz. So at DC, it is able to generate 50 kilovolt at DC and up to 500 volt at 150 kilohertz. Finally, at INRIM, with the support of University of Campania, developed an architecture for the generation of high currents, but with frequency components of reduced amplitude up to 150 kilohertz using suitable blocking elements to avoid the interaction between the generators. In fact, the first experiment done with two transconductance amplifier connected in parallel without blocking element shown this fact. This is a graph of the error between the desired current and at high frequency and the measured current. At high frequency, 150 kilohertz, the error is quite high. So without blocking elements, the error is quite high because the generators interact each other and a portion of the high frequency current flows in the low frequency generator is amplified and come back to the load. And this is why we have this so high error at 150 kilohertz. So attention should be paid in the design of the blocking element. So in conclusion, voltage and current transformers should be tested with distorted waveforms. Currently, standards about instrument transformer prescribe requirements up to 500 kilohertz, but do not give indication on how to test them. IT4PQ project established a metrological framework in terms of setups, procedures, accuracy parameters for the testing of medium voltage VTs and CTs up to 9 kilohertz. ADMIT project aims to extend the frequency limit reached in IT4PQ project, taking it to 150 kilohertz. And from a standard point of view, the working group 47 of the ICTC 38 committee created task forces to include the findings of IT4PQ project and the first finding of ADMIT about the IT frequency characterization in the standards. So I hope to have finished in time. Thanks a lot for your attention.
Thank you very much, Gert, for the invitation to present here. I want to start with thanking several of the earlier speakers of today because they have paved the way for my presentation as well. They gave an excellent introduction, so I don't have to explain all the details about harmonics, superharmonics, grid impedance, etc. I will slightly touch upon it, but don't go into all the details. So this is about electric vehicle charging stations, and the title is a bit a combination of everything. So it's industry and legal metrology perspective and metrology needs. So I will start with industrial needs and legal metrology perspective, and then show you some examples of work that has been recently done and is planned to be done in a particular project. Okay, yeah. I guess that most of you know VSL, so I won't spend too much time on this. We are the NMI in the Netherlands, and in contrast to most other countries, we are a private company. But nevertheless, we have 100 people working on metrology-related issues, and our focus is on energy and industry in general. So electric vehicles and electric vehicle charging systems, you might think that electric vehicles are quite new and very modern. It is sold that way nowadays. But in fact, as some of you probably know, electric vehicles exist already for more than 100 years. You see some pictures here. The picture here is from 1895. This is a UK design, and actually about 7 or 8 years before, there was already a full-scale electric vehicle in Germany, designed by Flocken, for those of you who know. And actually, this is also a nice one, because it was not only UK and Germany. France was also, by the way, heavily developing these cars, electric vehicles. And the US also followed. So this picture here is from Thomas Edison with his car, and this is 1913. And well, electric vehicles have had their ups and downs in the intermediate period. For instance, here in 1953, in East Germany, German Post had their buses or their vans. They were also fully electrical, and there were also some personal EVs like this one. This is the Henny Kilowatt in 1963, I think, 1961, something like that. So there were really commercial devices or commercial cars, electric vehicles already. And actually, this is also a picture there. We nowadays even have 3 lunar rovers, which are also electric vehicles on the moon. And of course, we have nowadays a lot of modern EVs that fulfill our expectations. So not only electric vehicles, but also electric vehicle charging stations are not particularly new. You see a picture here. This is from Seattle in 1973. This car is an AMC Gremlin, I think. And this is a public charging station. So, well, and in the right picture here, you see a public EV charging station in the Netherlands from Fastnet. They're popping up everywhere in the Netherlands. And well, they look much more modern, of course, but basically they're still the same. So from a market perspective, EV charging stations, I should actually say that these charging stations, they are developed because of their efficiency and their fast charging speed and so on. But there's a lot of problems that we've heard in previous presentations already that were not considered at all. So that's why we have started this work. But from a market perspective, as you know, electric vehicles are still expanding and growing. The market share is also growing. And the expectations here, 2030, 2040, 2050, are really growing exponentially. And we are talking about $8.8 trillion. That's 10 to the 12th dollars in 2013. So that's really a big amount of cars and money. And the charging infrastructure is still lagging behind. Most of the people that own an electric vehicle charge their system, their car at home. Well, if you want to go on holidays or to do longer distances, there should also be public charging stations. And the limited range of the electric vehicles is one of the key issues for manufacturers. It's still a few hundred kilometers only when fully charged. But for rolling out a large infrastructure of electric vehicle charging stations, the availability is a big issue. The availability of electric vehicle stations is a big issue for the owners, but for the grid operators, it's also a big issue because you cannot just plug in new or pop up new charging stations anywhere you like, because they have a big influence on the grid itself, and on there should be sufficient supply, but also power quality related issues. So one of the biggest problems in the Netherlands, for instance, I have drawn here a picture, but as we heard this morning from Sonja Berlijn, it's in many countries, it's already occurring, the grid congestion, which means that the grid is full, as we call it. So there's simply no more supply available to supply all these charging stations. And another issue is grid distortions. There's all kinds of regulations. I know from Europe, but it's also the case in other continents, areas. There's regulations on the amount of power quality. The grid operators are responsible to keep the voltage quality good, so to say. And so every new device connected or installation connected to a grid should have sufficiently low contribution to the power quality. And furthermore, there's safety issues and also the accuracy of the metering inside the charging station is an issue. So these issues ask for testing and measurement in general, and yeah, in this case, legal metrology is also involved, and standardization, of course, which I will explain now. I'm a scientist, so a scientific metrologist, so I'm not so much involved in legal metrology. It's a bit of a different world, as I will explain later in an example. So I had to look up the definition, which I want to share with you, because I guess there's more people that are not involved in legal metrology. It is regulatory requirements of measurements and measuring instruments for the protection of health, public safety, the environment, enabling taxation, and protection of consumers and fair trade. And it's about the regulatory requirements that the International Organization of Legal Metrology, the OIML, is responsible. And they have several technical committees. One of them is TC12, which is relevant for this topic. It's on instruments for measuring electrical quantities. and they issued a guide 22, 2 or 3 years ago, on EVSE, metrological and technical requirements, metrological controls, and performance tests. And that involves metering accuracy, EMC, so electromagnetic compatibility levels, environmental conditions, and durability and long-term reliability. But it's a regulatory requirement, and that's always a compromise between a lot of countries. So there's not a lot of details in these regulations. If I say it a bit strongly, then these regulations say that something needs to be organized, and they set the boundaries of what needs to be organized or arranged, but the details are definitely not in there. So they rely on standards. Another example, the OIML I just mentioned is the world level, so to say, the global level. In Europe, we also have regulations, in particular for European standards, equipment. And that's the MID, which is a famous directive in Europe, which regulates all kinds of meters that are used for billing purposes mainly. And a list can be found here, and one of them is active electrical energy meters. This MID is already 10 years old now, and yeah, so the discussion now is electrical energy meters. Do DC energy meters also belong to that? The formulation is such that you would say, well, maybe not, but maybe yes. And also EV charging systems, do they belong to that, yes or no? There has been a long discussion, and I'll come back to that in the next slide. So I just want to say also that if you fulfill the MID, then you get a CE mark, and the CE mark also shows then the year of affixing and also the ID number of the notified body, if that's the case. And as a clear example to help you illustrate this is a beer glass with a filling line of 0.4 liter, and well, such that you know that you get the same amount of beer throughout Europe. So as I said, I would come back to the MID. There have been a lot of discussions, and there is now an envisaged amendment to include actually EV charging stations explicitly, and also hydrogen refilling stations, and also smart utility meters, which is both for gas and for electricity. And actually, last few months there was a call for evidence, as they call it, and this was open to last. Or the second round was open to last weekend, the 3rd of March. And you could respond to that. And in the first round, I thought, well, this is a nice opportunity to show the metrology community has done a lot of work on this. So I thought, well, it might be a good idea to combine forces. And so I talked to Stefano as the chair of the EMN Smart Electricity Grids, and also involved the EMN on energy gases, and to come up with a combined statement saying, well, yes, we can show you we have done a lot of work, and we are fully prepared to provide the metrological background for this amendment. But then, as I said, I'm a scientific metrologist, so I'm not fully aware of all the political sensitiveness of legal metrology. And so I got a few responses, I should say we got a lot of responses saying that, well, we cannot give a combined statement because different countries have different expectations, different rules, but that actually did not refer to the statement that I wanted to make, but to for instance, the fact that an EV charging station should have a display showing the amount of money or whatever. That kind of rules. And countries and different cultures disagree on that. So, okay, so in the end, actually this escalated to the Euromed chairperson, and the final decision was, well, there's no consensus, so we cannot give a Euromed opinion. So, well, we just supplied it as VSL in at that moment. But it illustrates the difference between legal metrology and scientific metrology for me. And so it's much more political, and scientific metrology for me is just, well, science. So it's true or it's not true, or it's as true as possible. But yeah, that's it. Okay. Back to the story about EV charging systems then. As I said, there's regulation, which is very rough lines, which relies on standardization. And there's two particular standardization bodies that I want to mention. That's IEC, which we've seen before, and also SENELEC, which is the European standardization organization. IEEE also exists, but I'm much less aware of that, so I focus on European ones. Although they're quite similar, I should say. For EV charging systems or charging stations, there's 3 types of standards. The first one mentioned on top here, so that's this one, focuses on general requirements, and in particular the charging modes. One obvious charging mode, as I said before, is relying on home charging. Yeah, you can just plug in your car in your own socket and it works. And there's different control mechanisms. And the fourth mode is when there's an AC to DC conversion in the charging station itself. And actually that allows for much larger charging power. So then the second set of standards is related to metering. And that's these 4, just to mention a few. By the way, this is not extensive, so it's just some examples of standards that are there. But there's definitely much more. So that's about metering accuracy. There's quite some rules about that, standards. And the third set is about power quality. And that is about measurement methods, but also some characteristics and some limits. But these standards, again, well, ask also for testing and measurements. And in this case, they ask for traceability and metrology, which is the reason for starting a new project, a European project. And I should say that also standards and regulations, they're very, very slow processes because there's a lot of politics and discussion involved. And so if you want to start a new standard, that takes 10 years or so in practice. So so a lot of the newest scientific developments are not always included. And in the case of EV charging systems, the power quality up to 150 kilohertz, for instance, is not covered at all. And in general, testing in real world situations is not envisaged. I already mentioned a few times that we started a project. It's the MET4 EVCS project, also referred to by Stefano already. And this project started last year, so I don't have a lot of results from the project itself, but I do have some earlier developments to show. So it's funded by the European Union, by Euromed, and it's also supported by the EMN smart electricity grids. The consortium consists of 22 partners, and 13 of those are NMIs, mostly European, but we had a discussion whether it could also be outside of Europe. Korea apparently can also join. In this case, it's INTI from Argentina, who is also a full member of of the project, and funded. So, and then there's also 9 research institutes, mainly universities, but also 2 companies, and they're also collaborating with us. Or not collaborating, they're partner of the project, sorry. So what is this project aiming for? The overall aim is the development of metrology capabilities for the traceable evaluation of EV charging systems under realistic operating conditions. I now realize I forgot to mention we have the abbreviation EVCS, which is charging stations, but you might have seen another abbreviation in previous sheets sometimes, because they also use the abbreviation EVSE, which stands for supply equipment, but it's one and the same thing, basically. Anyway, so the first objective of the project is to define representative on-site operating conditions for EV charging stations, and that by that we mean up to 150 kilohertz and both the disturbances themselves and the grid impedance. And we promise to measure at least 5 DC and 5 AC chargers. The second objective is to develop traceable methods and test benches for the characterization of EV charging systems under these operating conditions that we just measured in the previous objective. And as you can see here, that means AC up to 44 kilowatt, but DC up to 350 kilowatt. And in particular for the DC charging systems, we expect to see more distortions because these are basically rectifier and inverter based devices, so they can inject a lot of distortions into the grid. These are laboratory measurements, so we aim for a target uncertainty of 0.1% under real world conditions. The third objective is to develop the required metrology infrastructure for on-site verification. So that's a bit more difficult, and therefore we aim for an uncertainty of 0.5%. And that includes smart charging and bidirectional charging, so also the EV feeding the grid instead of the other way around. And there's always the fourth impact objective, which I want to mention. That's to facilitate the uptake of the technology and the developments, and also of the measurement infrastructure that is developed, and to communicate that to the users. And in that case, that's the measurement supply chain, but also standardization committees like IEC TC 69 and also TC 13 about metering, and WELMEC working group, OIML technical committee, and the European Commission working group that's responsible for the MID. Okay. So that was about the project and its aims, but we did not start from scratch, of course. There's a lot of research that has been done in the past, and a few examples we have heard already in the previous presentations. But to summarize, a lot of work has been done actually already on EV charging and also on superharmonics in EV charging. Also a lot of superharmonics and even metrology of superharmonics, but the metrology of superharmonics from EV charging stations, that's a combination is new in this case. And that's what we want to do in this project. By the way, these are not all examples. These are just a few examples to give you an impression that a lot is done already. I also want to integrate the PhD thesis from ELAT and TU Eindhoven from Tim Slangen, which wrote a whole booklet about this. So as an example, some of you might have seen this before, as an example of the type of measurements that we want to do on site. I show you results that we have measured at the DC Grids project, which is just finished. And actually, it was measured at the DC site. It's important to realize that. I will come back to that. So it was measured at the ASR building, which is an insurance company in the Netherlands. And it's an open parking garage from a 700-volt unipolar DC grid, which can be operated in islanding mode or connected to the AC grid. And it has 3 EV charging stations, so it's really small. It's a trial grid, so to say. 3 PV panels, and also the lighting is connected there. And as I said, there's an AC to DC converter to link it to the AC grid. So we have developed a waveform recorder for this purpose, which consists of well, a voltage and a current recorder, which was adapted from 50 Hertz applications to DC. It has a mini computer with dedicated measurement software, and it is based on an 8-channel 12-bit digitizer, and it uses a voltage probe, which is very broadband, but we limited the bandwidth to avoid very high frequency to alias into the bandwidth of our interest. And it had 2 current probes, which we used. What we were particularly interested in is the ripple content, which is some kind of indicator or metric to see the AC content beyond the DC. So the DC is simply the average, and the RMS value contains everything. So the difference between the two is what we call the ripple content. You might argue whether this is ripple or not, but we have to give it a name. And it's mainly ripple still. So we did 2.5 hours of measurements, and it was a partially cloudy day with sunshine. So the PV system also changed its input, and we could measure different situations. We could measure different charging using the islanding mode or the grid connected mode. We could change the charging power. We used 2 different cars, and we investigated the situation where the solar, the PV panels were feeding the grid, and also where the EV was feeding the grid. The example of the waveform here is when the EV charging was started. So as soon as it started, the voltage dropped by 50 volt or so. This is apparently a very small grid with a very low inertia, which is to be expected for such a small grid. Some time-dependent measurements. This is simply the voltage and the current average over 1 second windows. So the DC current and voltage, and also the ripple. So in both of these pictures, this is the voltage and this is the current. You see on the right-hand axis the DC component, and on the left-hand axis you see the ripple voltage. And so here the blue is the voltage, and the orange is the ripple. And you can see here we were in islanding mode, grid connected mode, islanding mode again, and grid connected mode. All these large spikes were actually indicators of that something has changed, because when something is changing, then our definition of ripple is not so nice, and it gave a large peak. But anyway, roughly saying, the ripple content is remaining the same all over the measurements. A bit to our surprise, because if you do that for the current in this graph, you can see this was measured actually at the charging station. So here we were charging the car, and here the car was charging the grid. Again, here was charging with a different power, and again with a different power. But actually the ripple, well, it did change, but not that much. So a bit to our surprise, or maybe even to our, well, we would have hoped to see more. Yeah, once again, it was a DC grid, so there was no, there are no rectifiers involved in here in this system. So that might be the cause why it's so clean. Nevertheless, we did see something when we did the time frequency analysis. You can clearly see here, this is, by the way, from 0 to 2 kilohertz, and this is from 0 to 150 kilohertz with different resolution. And this is the time axis in both cases. And here you can see that when it's grid connected, that there is 50 hertz components. Also when it's grid connected, you see here in this graph that there's at 7 kilohertz and 20 kilohertz or something. There are really tones, but which were not there when it was not in grid connected mode. Anyway, the conclusion was that in this case there was no clear difference with or without charging. So it was a bit disappointing, but well, at least for this project it was. Of course, it's good for the grid operator, but not for us. So we did some further analysis, which I will not go into detail. We did it together with University of Campania, the group of Mario Luiso and Daniele Gallo. That focused on flagging and detection of events, and also on the compensation of slow amplitude variations. You can imagine that if you have a slope, that the ripple content will be wrong. Also, we proposed frequency groups up to 9 kilohertz and different groups up to 150 kilohertz, such that you do not consider individual components, but just groups of frequencies for easier interpretation. And also to do something on statistical analysis. And I should also mention that at EDF, which was a partner of the DC Grid project as well, they did quasi-peak detection on these measurements, but they found similar results as we did. So now I want to focus on measurements performed by UPV, which is a partner of the Met4EVCS project, but they did this already, mostly already before the start of the project. So they focused on the quasi-peak values. And as already mentioned before, they also found that the distortions, you can see it here, but also here, that it's related to switching frequencies and higher harmonics of these frequency of these switching frequencies. And for other cars, then they found, or for other EV chargers, I should say, they found that it was not highly peaked, but that there was a large broadband noise. And also when they zoom in, for instance, at one particular frequency, if you see that, if you then consider the time dependence, then you can see that there's an amplitude variation, which you can see here. And in the time frequency analysis picture, you can see it here and even better here, that you can see that the frequency is slightly shifting as a function of time, or actually it's moving back and forth as a function of time. And also, if you now take a cross section in this direction, then you see that the amplitude is actually moving, which is what you see here. Okay, so what did they do? And they will continue in this project, is to define synthetic waveforms for immunity testing of EV charging systems. So from the measurement results obtained, you can do amplitude modulation, or you can group particular sync functions that you find here. And you can do some filtering to make some more better well-defined reference waveforms for testing. And you see here different EVs measured by the same EV charging system. So what they also did is they considered several of the standards that are already available, and they realized that you might have to define different use cases, which sounds logical, but nevertheless it's good to define that. For instance, here are these measurement use cases, 1 to 5. You might compare conducted disturbances that you find in the grid with compatibility levels. That's one application. You might also do a statistical overview of disturbance levels in a network. That means how often do they occur, or per week, per year, whatever. You might also evaluate the thermal stress on equipment connected to the grid. So how sensitive is the equipment for heating by these higher harmonic components. You might detect maximum values in the case of impulse events, or some other metrics and in-depth measurements. And for all these measurement use cases, there's different frequency bands with different metrics. We have seen the RMS definition, like Deborah said, quasi peak or just a normal peak, and all these methods are actually defined already in either papers or existing standards. And I know this overview is in this paper, so you can look it up if you wish. Okay, so in this project they want to continue the measurements, had to define reference waveforms. And they are doing measurements in Bologna, the University of Bologna, where they have several charging stations and different cars connected. And they have another set of instrumentations, which I do not know much of the details about, but anyway. So this is a continuing story. Okay, and I also want to mention, I mentioned the PhD thesis of Tim Slangen from ELAT and at TU Eindhoven. We published a paper on this already. So what the question is, what happens not only when you have one car connected or one charging station connected to the grid, but if there's more. So what they did is they went to a place where they had more than one charging stations. 4 in this case, and used 1 at the same time, 2 at the same time, 3 and 4. And these are the measurements here in this these red circles here. And what they considered is the total superharmonic content. And actually that's something similar as the ripple content that I discussed before. And they also simulated what happens if you do if you add up all these signals. And what they saw is that the summation is not linear. And if you think about it, it's not illogical, because all these higher frequency components, they have a different phase and they might cancel each other out. And apparently they do, because we have seen, or they have seen, I should say, that it does not add up linearly, and it can even decrease after a few, after having more charging stations. And they gave for their simulations, they gave 95% prediction bounds, whatever that means in a simulation. But here you can see that if you have one charging station, the lower limit is about 4 ampere, and here if you have two charging stations, it might be almost 8. So it could double, but it could also just be at the same level, dependent on the details of the distortions. Okay. I mentioned ELAT a few times now. So ELAT is a facility in the Netherlands, which is built or constructed by the grid operators to focus on the EV charging systems and their influence on the electricity grid. And actually what they can do here is test all kinds of charging stations in combination with real cars. So you see here a truck, which is one of the biggest ones they have tested so far. And actually they have 360 kilowatt grid emulators, so they can provide a very clean signal. And they can also do that for controlled distorted grid conditions and for power quality testing. And they also have an EV and EV supply equipment or charging station emulator. for the communication testing and whether that still works in the case of power quality and also in the case of vehicle to grid. And they have a bidirectional DC load to emulate DC charging both ways. So the grid feeding the car and the car feeding the grid. Schematically, it looks like this. So we have the EV charging station here, and we have the AC grid emulator here. That's of course connected to the real grid. So it more or less cleans the grid, so to say. Then there's this communication device in between, and here is the DC grid emulator to absorb the energy and to feed it back into the grid, such that the energy is not really dissipated as heat. Because 360 kilowatts is quite a lot if you are heating your laboratory in that case. Okay. By the way, I should say more partners in the grid have similar, but maybe not completely similar, but comparable test facilities, like CEM has one, our Spanish colleagues, and also ITE, also in Spain, and there's more. But anyway, I want to focus on this one because I know this. So what do we want to do in this project? We want to measure the AC power in and the DC power out of the DC charging station. So we use our measurement system that I just showed before, connected here at the input of the EV charging system and also at the output. And at the same time, we might inject distortions at the input of the grid, of the charging station, and then to see what is the effect on the metering, for instance. We can do that with our own setup, as I said, but we might also just use other commercially available equipment that will then be calibrated or characterized by us in our laboratory. And I also should mention that the data analysis will be done by the University of Twente. That's the group of Professor Rietveld. I also received a sheet from, okay, I'll finish it. This is the last slide, almost the last slide. A reference system from Inti, which are developing, which is based on a phantom power approach. And they use their normal power calibration system also to measure EV charging systems with a load. Or at least they plan to do that. Okay, so the next steps are to define actually the representative on-site operating conditions for EV charging systems, and to develop traceable methods and test benches, as I showed some preliminary ideas already, and also to develop the metrology for on-site verification. And I should say that I focus now on the grid disturbances and ignored the grid impedance, but grid impedance will also be one of the things that we need to measure. Also, I would like to highlight that we have a midterm workshop at the end of 2025. There will be probably a hybrid one, so you could also join in person and online. And a final workshop with the project results in the middle of 2027, before summer at least. Okay, so that was what I wanted to show you. Thank you for your attention.